Hello, welcome everyone to this Tailing Dams webinar hosted by TC221. This TC on tailings and mine waste is one of the TCs of the International Society of Soil Mechanical and Geotechnical Engineering. So our approach to tailings dams is from geotechnical point of view. Okay. The TC221 began practically at the same time as the pandemic, which stopped our initiatives for organization of workshops face-to-face. So this is our first event online, and I hope we will have a very productive webinar. The moderator of this webinar will be Professor Cesar Pastén from University of Chile. So please, let's start this webinar, Professor Pastén.
Thank you, Professor Verdugo. Hello, everyone. We'll be moderating this webinar. Today's webinar will be structured in two sessions. At the end of the first and the second sessions, there will be time allocated to answer the questions from the audience, which can be shared through the YouTube platform at any time during the webinar. The first two presentations of the first session will set the general aspects of the discussion on the stability of tailings dams. These presentations will be delivered by Professors Jonathan Bray and Antonio Gens. Then there will be two presentations addressing the first question of the questionnaire that was passed along to the members of the committee, technical committee. The first questions regards to the design and maintenance of upstream tailings dams and the various geotechnical analysis required throughout the life cycle of these structures in order to ensure their long-term stability. Dr. Ramon Verdugo and Professor Antonio Carraro will be in charge of these presentations. The following two presentations will discuss the assessment of the residual or post-liquefaction undrained shear strength, considering current engineering practice and the theoretical basis in design. These presentations will be shared by Professor Fernando Schneidt and Dr. Arcesio Liscano. At the end of the first session, there will be time to answer the questions again from the audience that you would like to share in the YouTube platform. Then we will take 5 minutes break at about 2:25, which is in about 1 hour and a half more. Then the second session, we start addressing the third questions referred to the monitoring of upstream dams with potentially liquefiable tailing zones, identifying the most appropriate instrumentation to prevent flow failure. Professor David Williams and Professor Roberto Cudmani will approach this topic. Our two last presentations will be in charge of the engineer Luis Valenzuela, who will discuss the stability of tailings dams using the limit equilibrium analysis, and Dr. Mike Jeffries, who will highlight the need for more robust stress-strain analysis with appropriate constitutive models in support of the engineering design. At the end of this webinar, all the participants are encouraged to give their opinions regarding which of the topics presented today are the most pressing for the geotechnical practitioners in tailings engineering, since this will be a valuable input for the TC221 to guide its follow-up activities in the next months. Since we have a very tight schedule today, and since our speakers are very well-known worldwide practitioners, I'll just briefly introduce them at the beginning of their presentations. Each of them will have 10 minutes to deliver their presentations, and I will let you know 2 minutes before the time comes, just to keep track of time. So our first two presentations will be in charge of Professor Jonathan Bray and Professor Antonio Gens. Since many of you already know, Professor Jonathan Bray is a faculty chair in Earthquake Engineering Excellence at the University of Berkeley, California, Berkeley. His expertise includes seismic performance of earth structures, seismic site response, liquefaction, and ground failure. So Professor Jonathan Bray, whenever you're ready, please, you can start with your presentation.
Just confirming that you can see my slides and hear me. Hello? Can you hear me?
It's okay. You can start.
Okay, thank you. So thank you for Dr. Ramon Verdugo for organizing this and inviting me to share some of my thoughts on the system response considerations for tailings storage facilities. I am also, besides a professor at Berkeley, a steering committee member of TailEng, which is the Tailing and Industrial Waste Engineering Center. Advanced analysis plays a key role in understanding the response of a tailing storage facility. When an issue arises, you can be sure that this advanced analysis will be done to understand what happened. And therefore, before something arises in the design of a new facility or the evaluation of an existing facility, it is prudent to employ these advanced analyses to gain insight and understand the performance characteristics or the likely performance characteristics of a tailing storage facility. A key part of that is the constitutive model that captures the response of the material, and that has to be calibrated or captured through laboratory testing and field testing, as shown here. A reminder that one of the challenges we have in this system is the laboratory test results that are used to calibrate or to capture the in-state response of the tailings material so that it can be used to calibrate the numerical model that then is used to provide insight can be no better than the quality of the sampling. Undisturbed sampling with thin wall, smooth hydraulic piston sampler and Osterberg type sampler where special care is taken is critical to be able to capture the in-state response if we're going to capture that response in situ. The cyclic tests that are performed, such as a cyclotriaxial shown here, provide tremendous insight. And this is a test on a clean sand, a non-plastic silt, and a plasticity index equal 10 silt. You could see the shear stress versus shear strain response. And for these materials, we often see this for non-plastic and slightly plastic soils, their mechanical response is the same. What is often critical is beyond that, what you see in the laboratory test from just the stress strain response, but look at the water and how water moves in the soil. Sands reconsolidate very quickly and the volumetric strain is essentially appears instantaneously. Silts actually have a slower response. And you can also see the layering that you see even at the element level. And so when you start thinking about post-liquefaction residual strength, I see that as a system property, such as the famous back analysis of the lower San Fernando Dam, where it is the layering and it's not just the element response, but it's also the movement of water, void redistribution that then combine to lead to a back calculated post-liquefaction residual strength. And so it's my opinion that you should rely primarily on these back calculated post-liquefaction residual strengths based on field case histories, which are captured by such things as the cone penetration test, and consider the laboratory tests and interpret them with the context of understanding their limitations and thinking about things such as layering effects that may change the element response to the system response. One of the issues is a post-severe strength loss like liquefaction, static slope stability analysis to understand either seismically or statically if the soil is likely to trigger liquefaction, what are the consequences? The post-liquefaction static slope stability analysis. Although advanced analysis should be performed, before you perform those advanced analysis, I think it is useful to gain insights from limit equilibrium analysis. They can provide valid insights. They can give you a sense of the performance, a sense of the answer before you do the more sophisticated analysis. And in some cases where things are fairly straightforward, they can be used as a screening analysis. With the residual shear strength for a strain softening material, it's common in practice to use a post-liquefaction static factor of safety with these residual strengths for the liquefied material greater or equal to 1.1 to 1.2, considering things such as how brittle the response is, the uncertainty in the characterization, and the consequences. We need to start moving toward true performance-based engineering approach where we characterize the risk and think about the cumulative effects of uncertainty in the geometry of the groundwater, the soil properties, the hazard assessment, the testing analysis, and I think that there's opportunity to do that. Talking about the pseudostatic slope stability analysis, it is not possible to capture the sophisticated, complex response of a system to a ground motion with a single parameter, a seismic coefficient. And so one has to think about this as being a calibrated approach that is just providing that initial insight. The seismic coefficient represents the seismic loading, the strengths are captured, and the factor of safety. We have to talk about all three of those together. And a selection of an acceptable combination of the seismic coefficient, the strengths, and the factor of safety has to be required through back analysis of field case histories to get consistent performance, or when those are lacking, consistency with more advanced analysis. The idea that a factor of safety of 1.1 is safe is not appropriate. It depends on the seismic coefficient, the strengths, and how the analysis is performed. And so given the importance of the seismic coefficient, it should be characterized carefully. It clearly depends on the earthquake shaking, the intensity, frequency content, and duration, and it depends on the dynamic response of the actual tailings storage facility. But it should depend on how critical the structure is, and really that leads to what's the acceptable level of seismic performance. And we typically look at that in terms of allowable displacement if we're going to have limited displacement. And so a pseudostatic analysis, in my view, it's more straightforward to use a factor of safety greater or equal to 1.0 and then calibrate that seismic coefficient against the displacement that you're going to use to judge good or bad performance with consideration of proper strengths. You know, the work I did with Jorge Macedo, building on the work with Aya Travezero, developed a method for estimating seismic displacement as a function of things like the yield coefficient, the dynamic loading, the spectral acceleration at the degraded period of the system, and such. That can be inverted so that you can get a displacement allowed, calibrated seismic coefficient that will give you a consistent performance with what you would have gotten if you had done a seismic displacement analysis. It also includes the seismic loading considerations and, importantly, uncertainty. Just using an example, let's look at a seismic coefficient for magnitude 7 earthquake. I'm calculating the seismic coefficient for different spectral accelerations based on the loading. So if I just pick a displacement of 15 centimeters, you can see as the loading increases, the seismic coefficient is going to increase. Let's pick one ground motion level, a spectral acceleration of 1G at the degraded period of the site. This is for a system that has a period of 0.3 seconds, and it's a magnitude 7. Depending on what you consider allowable performance, whether it's 50 centimeters, 15 centimeters, and 5 centimeters in this example, will lead to a different seismic coefficient. So the seismic coefficient just doesn't depend on the intensity of the ground shaking and the duration, the magnitude. It depends on the allowable level of displacement. If it's 50 centimeters, it can be a relatively low number like 0.08. If you have very stringent criteria and 5 centimeters, the seismic coefficient would be 0.34. So in conclusion, this method only should be used in non-flow cases. A static post-liquefaction factor of safety has to be greater than 1.0. You should use strain-compatible post-shaking strains. The important thing to predict is selecting an allowable level of shear displacement and the uncertainty that you want to capture. Capture the dynamic loading and then select that seismic coefficient, not arbitrarily, but based on the ground motion, but very importantly, the level of displacement that you consider to be acceptable, and then calculate a factor of safety greater than 1. That's essentially consistent with calculating the right displacement less than that value. You remember that Newmark analysis captures shear, so you have to add in the volumetric induced displacement to get the total displacement. Another way of going, which is not much more complicated, is instead of using a calibrated seismic coefficient, just use a seismic displacement analysis, or move toward performance-based probabilistic analysis, where you capture the uncertainty in the ground motion, you capture the uncertainty in the dynamic response of the tailings storage facility. And a paper such as that by Macedo et al. 2018 provides some insight on that. Thank you.
Thank you, Professor Jonathan Bray, for your presentation. Now we will go to the second presentation of the day, which will be in charge of Professor Antonio Gens. He's a full professor at the Department of Civil and Environmental Engineering at the Universitat Politècnica de Catalunya, or Technical University of Catalonia, Barcelona, where he has developed a successful and very prolific academic and professional career. Professor Gens, whenever you're ready, please start your presentation.
Okay. I'm sharing my screen. So hopefully you should see my presentation now. If not, tell me, but I'm assuming you are seeing it. So thank you very much for this invitation, Professor Verdugo, to this TC221 webinar. I was given quite a lot of freedom to choose my subject, and I want to share some thoughts about the role of instrumentation, perhaps with a bit of a wider perspective in the context of brittle failure. Brittle failure will occur, I'm going to change the pointer, will occur when we have brittle materials, obviously, or brittle components of the system. I'm very simply defining brittle as a material in which, after reaching a peak strength, it will reduce to some sort of residual. And it's very well known that brittle failure occurs without previous warning in many, many occasions. I'm just going to give you a couple of examples. This is a tailing dam that fell, but it's not an upstream dam. In fact, it's a downstream one, rockfill dam, so probably the safest you can build. But in spite of that, it actually fell because there was a sliding on the clay that was in the foundation. And that clay was actually very brittle, as we can see in this ring shear test carried out on NGI, in which the peak reduces significantly down to residual. In fact, there was liquefaction of the tailings behind it, but this liquefaction was after, as a consequence of the failure. It was important because it provided the extra thrust to move this dam something like 60 meters downstream, opening the breach and allowing the tailings to flow out. The dam was instrumented, and there was an inclinometer just in the section where it fell. Here, coming from the original report, as a matter of fact, there were no measurements in the weeks preceding the failure, but the last measurement is this one here. We can see a couple of millimeters here of displacement, and now that we know where the failure took place, it's exactly at this point. But I think it would be, you should be very sharp-eyed saying that this is the precursor of a catastrophic failure. In fact, we did many analyses because we were the expert witness for the court, and all the analysis pointed out that even if it had been measured, the movements in this critical section would have been very small indeed. This dam was actually closely watched. So every 2 weeks there was an inspection. Somebody went there and actually filled this form. You cannot see, but actually if I translate it in here, it's nothing noticeable, all quiet, no cracks. The interesting thing that the date was the day before the failure. In fact, a few hours before the failure, because it was in the afternoon and the failure took place at 3 in the morning. So no warning whatsoever. The second case, it's a well-known case, Carsington Dam, a water dam, which was near reaching end of construction. It fell about 600 meters long. It fell through the core and through the clay in the foundation, the yellow clay, and it was also instrumented. These are measurements of the horizontal displacements at the toe, and you can see that there is a very sharp increase associated with the failure. There was very little warning, perhaps 24 hours, but it was a weekend, too late to do anything. So, and in the case of flow liquefaction, which is a kind of ultimate brittle failure, we have the case of Brumadinho, which there was the failure with no apparent precursors. I'm not going to talk about Brumadinho because later on, I think Professor David Williams is going to go back to this case. But yes, I wanted to bring this picture. The expert panel did a good job in analyzing all the seismic records, many associated with blasting. The one here on the left is the one corresponding to the failure. Here in red is the moment in which you can start seeing perhaps some signs of failure. And we can see that the start of this event was just a few seconds before. So it's not a warning system at all. I bring this here because 6 months before, there was a very similar event happening, very different from the blasting ones, which was associated to the drilling of a sub-horizontal deep drain. And we have reasons to believe that this drilling actually set off a kind of a contained liquefaction that didn't propagate to full failure. So having records like that, can you perhaps give you an indication that you have a part of the dam which is very close to liquefaction? Obviously, if this is going to be associated to the failure, then it will not be of any use at all. So my opinion is that there is actually little chance that there will be a monitoring system giving adequate warning of impending flow liquefaction failure, even if we resort to quite advanced technologies. And I think instead we should focus on trying to identify whether we have liquefiable materials in our system. And for liquefiable materials, we need two conditions. The first one is that the material should be saturated or close to saturation. Sometimes the figure of 85%, 90% is put as a threshold over which there is liquefaction, although the empirical basis for that is rather scarce. And also that the material should be brittle. I mean, not all contractive materials are brittle, so we should try to identify when they are brittle. How to identify saturated materials? Obviously, deploying piezometers is the obvious answer, but how many? Because there may be, depends on the case, but in some cases there may be big variations in on the extent of saturated materials or close to saturated materials. And also piezometers may miss these unsaturated but close to saturation zones that may liquefy. An alternative, which was not mentioned very much in the answers to the questionnaire, is the measurement of P wave velocity. Again, it's very sensitive, but it's only very sensitive when it's very close to saturation, over 95% or so. But it has proof that it can work. These are results from Jamielkowski in that big Polish tailing dams that he and his co-worker have been working for many years. You can see that it identifies the water table, identifies the Perth water table even, so showing that there are some complexities in these distributions, but it's always difficult to know whether if you have an intermediate value of peak wave velocity, whether that corresponds to a liquefiable material or not. And finally, the final point is how to identify brittle materials, and usually resort to in situ tests, and CPTU tests are the favorites. Vane also, but I tend to prefer CPTU tests, interpreted in a fundamental way through the state parameter, or more empirically using soil behavior chart types. I just want to mention that we are interested in this, in our group, we are interested in this question, and we've been trying to do modeling of cone penetration in brittle materials and try to provide a better understanding and to try to identify a signal that can be related to the brittleness and ideally to the degree of brittleness. We use a model, as was mentioned by Professor Bray before. This is a different one based on critical state and state parameters. We take into account that we deal with softening materials with large displacements, and basically we push a cone with different materials. This one would be contractive but not really brittle, and the brittleness keeps increasing until getting to this one, which is very brittle indeed. And these are some of the results that one can obtain. Here you can see how the formulation is refining the mesh following the advance of the cone. The pore pressures are more or less a steady state. There is a reduction of stresses. Anyway, you can actually look at it and try to understand and try to get some results. And this is my final picture. For instance, these are the range of results that we obtain with these different brittleness. These are the usually normalized parameters of cone. We see the reduction in the cone resistance, the increase in the pore pressure coefficient, and so on. There are many results like that we published last year, and we are going to show them more in the CPT symposium this year in Italy. And I think my time is up. So thank you for your attention.
Thank you for your very interesting presentation, Professor Jens. For those of you who are not familiarized with what motivated this seminar, this was motivated by answers given to a brief questionnaires of some of the main geotechnical issues related with the stability of tailings dams. A significant number of those responses showed serious divergences on key aspects related to the design, analysis, and monitoring of tailings dams, prompting the organization of this discussion session. The first question of that questionnaire is it possible to design upstream tailings dams where their stability can be guaranteed on a long-term basis? If so, which are the basic requirements that an upstream tailings dam must meet? These questions will be discussed by the following two present speakers. The first one will be Dr. Ramon Verdugo, who got his master and PhD from the University of Tokyo. He's currently the chair of the TC221 and founder of the geotechnical engineering consultant firm GMI Limited. So Professor Verdugo, please, you can start with your presentation.
Thank you, Dr. Pastena. I'm trying to share the screen. Can you see my screen? There is no answer. How may I know that you can see my screen? Well, I will start. Well, the question is, the first question is whether it's possible to really trust upstream tailing dam. But my approach is, or my response was, it's very difficult. Here, this is one example, Barahona upstream tailing dams that failed after the earthquake or during the earthquake of 1928 of magnitude 8.4. You can see here the surface of the surface of the failure. Clearly, this was a very catastrophic failure. After that, in Chile, we had this one in 1965. 5 as another earthquake of magnitude 74 destroy or trigger the failure of Cobre upstream tailing dams. And this is another example in Japan. Mochikochi upstream tailing dams, dike number 1, failed after 10 seconds of the main shake. And very interestingly, the dike number 2 failed 1 day after of the main shock at a quiet time without any tremor. They have some accelerometer and they are pretty sure that there was no tremor at the time of the failure of the dike number 1. The 2 previous tailing dams that I showed, Barahona and El Cobre, these 2 tailings failed after the earthquake. In one case, 2 minutes after, in the other case, some seconds after. So the earthquake is not really, the inertial forces of the earthquake are not really the forces that trigger or create the failure. Something happened that is triggered by the earthquake that finally end up with the failure of the dam. This is another case, Brumadinho. Now, Professor again saying that some small tremor may cause the failure. And you see here how is an upstream dam. Okay, these small dikes with competent material, but are resting on the tailings, which can be absolutely loose or in a very contractive state. The first data showing the static liquefaction are provided by Dr. Castro in 1969. And here you can see his results. First, he, using a triaxial test, he put the sample and then apply dead load and in an undrained way. And it took him 40 minutes to reach the big value, and suddenly the sample failed. And in 0.18 seconds, the samples deforms to almost 20%. So here you can see peak strength and residual strength and the increase in the pore pressures. Okay, so this is a very important that this failure occurs suddenly, and you have a drop in the strength, and the sample will really flow because the dead load is larger than the residual strength. This is another just result of undrained response of sandy soils at different confinement, an identical void ratio after the consolidation. So you can see here that if the void ratio is the same in an undrained loading at different confinement pressure, the stress strain curve are different. However, the ultimate strength is just the same because it's associated with the void ratio. If you are at low confinement pressure, the sample will be very dilative. However, if you are at sufficient large pressure, you clearly see the contractive response reaching one particular ending point, which is the steady state or the critical state. Here are the results for this particular sun of the steady state line. So in the upper portion, you see contractive response of the material in undrained condition, and also below, you can see clearly a dilated response of the sample. So the steady state line will divide the contractive state from the dilative state. Okay. So doing triaxial test, simple shear test, you can find this line and you can define more or less or find the ultimate strength. However, in the case of tailing, where the sample or the soil is really stratified, that's one question. How can we trust the value that we are getting in the lab or from a field test? One other important aspect is all the data suggests that the monotonic effective stress pass control the collapse of the soil. In the left figures are result of monotonic load, the one with the peak, and cyclic test, which were performed in order to don't pass the peak. And clearly you see you don't pass the peak. However, you touch the effective stress pass of the monotonic load and you go down immediately to the residual strength. So a small earthquake may trigger liquefaction without passing or bypassing the peak strength. On the other case, data from Sathidaran in 1983, he performed this very interesting testing. test. This is a normal triaxial test and drain test up to here. He increased the back pressure in order to make it equal to the pore pressure. Then he increased only the back pressure, simulating, for example, the rise of water level that increased the pore pressure, and the shear stress is maintaining constant. So the sample is moving with this effective stress pass under drain condition, but suddenly it collapsed. And although the valve in this case of the sample were open, the collapse of the sample was so fast that the behavior of the soil of the sample was absolutely undrained, because it takes few seconds to go to the failure. So small tremors and just rise in the water table may cause the failure of the soil if it is in a contractive state, such that the static shear is greater than the residual shear strength. And this is the condition for a flow failure: soil in a contractive state plus the static shear stress greater than the undrained residual strength. The static shear here, you can arrive to this static shear in a drained way. So if we continue in a drain condition, we should move through this black line up to the drain strength. So you are somewhere here, and if something like an earthquake or a rise in the water table trigger the undrained response of the soil, you will move to this point without passing through the peak. You will be here, and then immediately the sample or the soil or soil elements will respond in an undrained fashion, and the undrained residual strength will be mobilized. So in this case, you have a static shear or permanent shear or driving forces that is greater than the strength, in this case, the undrained residual strength. So if you calculate the safety factor, 4 will be smaller than 1. But in a drain condition, if you use friction angle and cohesion for the analysis, you will have a very nice safety factor. So when you are looking drain condition, it's a perfectly stable, but when you look the undrained condition, you will have a collapse of the sample because of the soil, because the permanent shear stresses are greater than the strength of the material. So my concluding remarks are: the empirical evidence indicates that the number of upstream dam failures significantly exceeds the failures of both downstreams and centerline tailing dams. However, we have also some failure in center line, like some Mount Polley, but in those cases were because of problem in the foundation soil or because of overtopping. Typically, the construction of tailing dams is part of the operation. Therefore, problems in the operation directly affect the result of the construction. So it's different than the ordinary civil work, because operation is construction. Okay, so to control operation is very complicated. Yeah, it's much easier to be aware of what is going on during construction, but not during operation. Unfortunately, in upstream dam, there is no room for errors in the properties and behavior of the slimes that support the resting dikes of the dam. Commonly, the storage slimes are loose in such a way that they present a contractive response. Therefore, any disturbance that generates the undrained response of the slimes can trigger the liquefaction and the consequent failure of the upstream tailing dam. Finally, it is possible to state that upstream tailing dams have an inherent susceptibility of failure. That's it.
Thank you, Professor Verdugo, for your interesting presentation. Apparently, there is still a problem with the chat, YouTube chat. We haven't received questions yet. So please, to the organization, if you could activate the chat in YouTube so we start receiving the questions and comments from the audience, would be great. Please help with that. Our next speaker is Professor Antonio Carraro. He earned his PhD in civil engineering from Purdue University. He's currently a senior lecturer in experimental geotechnical engineering, the Faculty of Engineering, the Department of Civil and Environmental Engineering at Imperial College of London. He's a UK nominated member of the TC 221. So Professor Carraro, whenever you're ready, please, you can start with your presentation.
Thank you very much, Cesar. I'm sharing my screen. Could you confirm whether or not you can see it? All right, so I hope that everyone can see the same thing that I'm seeing on my side. First of all, I wanted to say many thanks to Professor Verdugo and TC221 for this invitation. My role today is to try to articulate and summarize question one that Professor Verdugo has already briefed in his presentation. So that's going to be the first bit or part of my presentation. If we actually break question number one into the two sub-questions, we'll see that by looking at the responses from the survey, we have a generally optimistic response, perhaps, from the group of respondents, indicating that about 2/3 of that group suggest that it is possible to design upstream facilities in a way that their stability can actually be guaranteed on a long-term basis. However, if we actually look into the answers in a bit more detail, we're going to find out that there's quite a few follow-ups or caveats associated with those responses. So if we then move towards the second part of the question and inspect in a bit more detail what those requirements really are, then you can see that things become much more specific. So if you try to break into those requirements into groups, you find that many, or perhaps quite a few of the answers, they were suggesting that those facilities are okay as long as we're looking at a particular set of conditions. So for example, flat, desert-like, low seismicity regions. If we next pay much more attention in terms of design details, you'll see that there will be an important group of responses that would be requiring rigorous and sound analysis to be associated with these types of facilities. One respondent suggested a competent designer to be in charge. That sounds like fair game, as well as strict rules, best practice, and so on. So all that being fundamental aspects of the design of these facilities. There's one answer associated with the requirement for adequate foundation, which is probably a reasonable limit state as long as we're also clearly identifying liquefaction as an alternative limit state as well. And then we look into the perhaps more detailed aspects of the operation and maintenance of those facilities that also relate to design, control deposition, the details of the structural zone that in the end would probably suggest that these are actually much more complex structures than we might otherwise think. One thing that showed up quite a few times was the issue of drainage. So really we're looking at facilities that will have to have a very comprehensive drainage system below, above, inside, in such a way that phreatic surface, as well as the issue of liquefaction, at least from a static standpoint, could be somewhat controlled. And then finally, the more general aspects of stability, if things go wrong, some kind of redundancy with additional structures to really provide some kind of insurance policy, if you will, associated with the design. Finally, if we move into the other aspects related to construction, operation, and closure, you'll see that construction and operation is really highly emphasized in terms of quality control. So quite a few of the answers, they focused on issues related to quality control and following rules and best practices. The operation being ideally associated with good governance, management, but also that the observation of those design requirements will have to prevail throughout the process. There are also questions or answers associated with instrumentation and monitoring that will be addressed in question 3 later, so I'll leave that for the follow-up discussion. Just to then finish up these summary responses, then one answer also pointed out the issue of a mandatory walk-away design. So really an idea that if you're going to walk away from the facility, that will have to be a stable set of conditions that would prevail afterwards. So that's hopefully is a little bit of provide a little bit of an insight about the actual responses coming from the survey. The next bit that I wanted to really illustrate before my time is up today are really questions associated with the more basic fundamental aspects of these facilities. So from a more general standpoint, if we focus on the aspects related to design and construction of upstream facilities such as these, normally we know that these facilities, they are constructed in stages. We eventually, at some point, get to the point that we reach the capacity of the facility. And you can see that we end up with a structure that is a hybrid in terms of aspects or locations within the structure that are relatively well controlled, and then other regions that may not be necessarily perfectly controlled. So from a storage standpoint, that's obviously a design that is great. So we can definitely maximize storage within this setup. But then the question becomes, from a geotechnical design standpoint, is this really a sensible approach? So if we have an analogy in terms of similar things that are inherently unstable, for example, if you get a balloon filled with a certain material, in this case, a well-defined liquid, and you start to play with that, as I did a few days ago, you'll find out that sooner or later, it's likely that a balloon eventually is going to burst or no longer exist. That's exactly what happened to me. Luckily, that happened at a point where the balloon was already outside my office. But nevertheless, we are really looking at, I believe, in these types of approaches with a design that is inherently unstable just because of the geometry of the design. But then to me, a more fundamental question relates to the actual aspects of the behavior of the materials that we're actually dealing with. In the case of the water-filling balloon, I do know that I have a liquid inside that balloon. What can we actually say about tailings? And that triggers in my mind perhaps a different type of exercise in which perhaps we need to look into the design process from a different perspective. So if we look at a typical example of a process of design, such as the one that you see on the screen, it's very obvious to see that due to the nature of this in-series protocol, you can see that any limitations or any issues associated with any one of the steps along the process will eventually, like it or not, have an impact in terms of the final results. So one question that I think it's important to then highlight or emphasize is whether we know or are aware of any particular issues that could be then specifically associated with the construction or design of upstream slurry tailings depths. And then maybe a side question would be related to how much we as geotechnical engineers, not just the mining engineers, but we as geotechnical engineers are really aware of those issues and limitations. So those are the kind of things that I thought would be perhaps worth exploring a bit further. So I'm going to essentially just point out 3 elements of specific parts of this process that I thought would be useful sharing. The first aspect could be associated with a very basic idea going back to fundamental soil mechanics. So if we are, for example, interested in the assessment of key states of the behavior of the material, for example, let's say a phase transformation state, and we go back to a set of triaxial responses that we can control in a laboratory, then we would know that in theory, if our model is a model that's based on the idea that density and stress are the key state variables that we need to be aware of, as long as we're able to control those 2 variables, we will have to have a response that will be systematic or relatively consistent a priori. But in reality, if you actually look into the way laboratory testing is carried out and normal practices, we do know since at least 4 or 5 decades ago that soil behavior, the behavior of geomaterials, is actually dependent on fabric, not just density. So if you repeat these experiments 10 times, 20 times, 100 times, you are going to find systematic differences between the responses that you're measuring, primarily because of the way or the process used associated with the sampling or reconstitution that we're actually using in those procedures. A second aspect that I think it's also directly related to the interpretation of the very classical laboratory response, which to me seems to be even more overlooked, it's really related to stiffness. So if we go back to those same 2 conditions that we had before, look at states that are relatively similar in terms of density and stresses, then we're left to behavior that is inherently dependent upon the methods and the techniques that we're actually using or following in our laboratory or analysis procedures. Once again, the reason for that is because what really controls the behavior of these types of geomaterials is not only the density, but also the arrangement that exists within the samples or specimens that we're actually testing. Regardless of the testing protocol that we're using, that's always going to show up in a systematic way. This is not a random observation. This is a systematic outcome of the processes that we are using. Last but not least, I think one of the things that always come back to my mind that I think we need to probably scrutinize a little further is the issue associated with the possible or perhaps relevant states that we're actually dealing with. So in a similar fashion to everything else that we do in terms of mapping mechanical response, whatever we implement or use will have an impact in terms of the outcomes of the things that we're measuring. So if we're interested in, or we are in the business of assessing states in a way that resembles the types of applications that we are interested in, I think we need to have a much more in-depth conversation about how those states are actually being produced. Is in this particular case, we're not just looking at specific details about the testing procedures itself, but also the expectations that we have in terms of how we define those states. I think we need to think of this not only in terms of very specific scenarios in terms of only density, but open up that kind of analysis for broader capabilities or broader possibilities that take into account possibilities in fabric as well. So I think these 3 items, which are essentially very basic aspects of the fundamental behavior of geomaterials, could be things that in our process can lead to quite a few important outcomes in terms of the analysis that we carry out at the end. So just as a summary, even though the responses from the survey, they appear to be a rather optimistic view of this type of design approach or method, upon further inspection, you'll find out that there's actually quite a few requirements associated with those answers. So perhaps all those yeses, they may not be straightforward, positive, supporting answers, if you will, once we look into the details. The nature of this design is inherently tricky. So you know already the way I personally think of upstream facilities. But I think then the next question really is about what we can actually do in terms of raising the bar and increasing the level of understanding in such a way that we can move this design to a higher level in terms of understanding and articulating final answers for that. Last but not least, not only, in my opinion, the state of the practice needs to be improved, but also the education associated with fundamental geotechnical principles. Those two are issues that come along and come together. They are inherently related, and I think we can actually, or we should be thinking much more seriously about how to do that to raise the bar. I close today by saying thanks to my colleagues and collaborators here in London. I'm very grateful for all their help and assistance, and I look forward to questions that will possibly happen at the end of this discussion. Thank you very much.
Thank you, Professor Carraro, for your interesting presentation. Now we will discuss the second question of the questionnaire, that is, which are the most appropriate procedures to evaluate the residual and drain shear strength of liquefied soils in the laboratory and in the field. For addressing this topic, the first speaker is Professor Fernando Schneid. He's a professor in geotechnical engineering at the Federal University of Rio Grande do Sul in Brazil. His work mainly focuses on soil structure interaction, geotechnical characterization, and behavior of geomaterials. Professor Schneid, please. Your microphone is not connected, I guess. So if you could activate it, please.
Yep.
There it goes.
It's activated, yes, and I'm having problems. Slides, let's see if it helps me here. My computer. Give me a second, let's see what's going on here.
So in the meantime, I will remind all of you to share your comments, thoughts, and questions in the YouTube chat. It's already available. So we have gathered some questions already, but feel free to share your thoughts with us. After these two following presentations, we will discuss some of them until half an hour more. Is 12:30. It's 12 now in Chile and Brazil now. We will be discussing these questions at about until 12:30, more or less. So
Okay.
now it works. Thank you, Professor.
It works. Okay, glad. I'm glad about that. Here we go. So I'm very happy to be here. TC221 is actually up and running, and it's good to have this first webinar for TC221. We have been hearing a few presentations before highlighting the need for very advanced analysis for dealing with these tailing materials, and now I think that I have to sort of step backwards and going back to the prediction of a of the residual drain shear strength, either from lab and in the fields. And there are pros and cons, and we have seen that on the answers that have been given by our questionnaire. But it's very difficult really to take a side on it because, to my understanding, there are a set of unresolved issues on deriving this parameter, and there are severe limitations to the way that we approach that into design. So I'll try to have some insights in respect to that, based on the answers to the webinar. I think that the first point, and I think that's an important point, is recalling that most of the methods of predicting the drain shear strength are based on critical state soil mechanics. So there is a good side on it. But from what we've seen, this is a very controversial issue. And by looking at all the answers, I was trying to find out why the assessment of the drain shear strength is so controversial. And I think I came out by looking at the answers with three main reasons for that. The first one is actually that the prediction of the drain shear strength is related to limit equilibrium analysis. And there is a confusion in the literature over SU, and this confusion is very much related to the fact that this is an input parameter for limit equilibrium analysis. And we know that we've heard about the limitations of using this type of approach for materials that exhibit strain softening and therefore progressive failure. I'm not going to get into details about this because this is the one issue that's going to be discussed later on by our colleague Luis Valenzuela. The second point, I think that we've got to go back to the basics and look at the actual definitions of residual shear strength. We've been using that in several different ways. And the third point is that it relates to different mechanisms, at least those associated to flow or cycle liquefaction. So let's put that into perspective in order to see whether we think that we are able or not to produce reasonable predictions in terms of interpreting data for estimating this parameter. When I was talking about definitions, there are several methods that are currently adopted for estimating the drain shear strength or the post-liquefaction of drain shear strength. So the first point is really, let's look at what we're saying, and this is not new. If we talk about ultimate shear resistance, we are on the safe side because we can measure that in an undrained monotonic lab element tests. We can be talking about critical state strength or steady state strength, and we can do that using reconstituted samples in the lab. That's not a complicated issue. We've seen on the previous presentation that everybody's mentioned this as a residual shear strength. And it corresponds to the available post-peak strength determined from undrained monotonic or cyclic lab element tests. So in this sense, I think that we are kind of safe as well, but there are some drawbacks because we might have to approach this problem using undisturbed samples, as suggested by Professor Gray early on. And then there is a third definition that's related to this liquefied shear strength. That's a bit more complicated because it refers to the shear resistance that a liquefied soil mobilizes in the field. And that's why it's so complicated, because this is not replicated in lab element tests. That's one point. And that's not even within the field of soil mechanics. That's a kind of combination between soil mechanics and soil rheology. So here we are not in very safe grounds. So this is one point. So I'll sort of try to put that into perspective as you go along. The second point is that we are talking, and we've seen in the presentations, Professor Ramon that is in Chile talking about cyclic liquefaction, and whereas others were referring, for instance, James to Brumadinho, in which you're talking about flow liquefaction, the one triggered by monotonically increased shear load, whereas the other is triggered by cyclic loading. And despite of that, both phenomena are related to development of very large strains, and that really corresponds to the strain softening behavior of these materials, and is accompanied by excess pore pressure being generated under undrained conditions. So there are different approaches when we are looking at these two different phenomena. So I think that's important, and I was trying to do that when reviewing what was being presented in the answers to the questionnaire. I was trying to review and trying to organize the ideas. And what we could see is that for high-risk projects, and that's embedded in standards and regulations, there is a need to measure the undrained shear strength from either cyclic direct shear, simple shear tests, the DSS, or cyclic triaxial tests. And that's the reason why, when we saw the answers, we've seen a large number of different lab techniques being adopted, and triaxial tests and DSS, the cyclic tests, have a predominancy on the answers exactly in the areas in which we are dealing with high-risk projects. So, okay, we understand that, but then we cannot take that for granted, because when doing this type of analysis, we need high-quality, undisturbed samples. And this is a major task, a major challenge when we're dealing with this silty, non-plastic, saturated materials that are prone to liquefaction. Then we don't have real experience or gather real experience in the same way as you have in clays or even in sands. There is, for instance, one research activity that's going on in Brazil now, that's being developed within the major mining industry in Brazil, in which undisturbed samples are being retrieved in one of these reservoirs with materials that show high susceptibility to liquefaction, and we are using the gel push sampler, the 6 inches stationary piston, the Oysterberg, Laval, and even soil freezing from one of these techniques. So it's very important to really understand in which extent the fabric is being preserved when retrieving these undisturbed samples, as pointed out in the previous presentation by Dr. Carraro. So this is one of the points that we have to bear in mind when dealing with these high-risk projects, which are essentially based on lab tests. In some cases, we are using reconstituted lab tests, and of course, there is again the problem that has been mentioned before about how to select appropriate materials, and there is always a need for a combination between in situ and lab tests, the one for evaluating the spatial variability of a reservoir, and then selecting the appropriate materials for doing this type of analysis. Now, as we move to from high risk to low and medium risk projects, then it's a different matter. Then the in situ tests, they start to have some protagonism, if you like. And we've seen many of the answers that were placing more emphasis on in situ tests than on lab tests. And this really have to deal with the fact that we are dealing with these low to medium risk projects. In this case, we can use we can use in situ tests in a number of different ways. For instance, if we're talking about cyclic liquefaction, there are several methods that have been developed for measuring or for estimating, for predicting the cyclic resistance ratio, CRR, and the peak and drain shear strength. This is a pretty conventional type of approach that are used for clays, and that we can extend it for silt descents, provided that rate effects are properly taken into account. If we move from the peak shear strength to the residual shear strength, and you are under cyclic conditions, we can estimate this residual undrained shear strength as a percentage of the peak strength. And that is related to experience that we have gathered under cumulative strains over a number of cycles in cyclic liquefaction. So you see that the choice for lab or in situ tests, and they always come together, but the choice is very much related to the seismic conditions of a given site. If you look about the answers and given by the questionnaire, we see again a large number of different tests that are currently used in practice, used and recommended. The CPTU is a dominant technique, not only because it gives some ways of assessing the undrained shear strength, but essentially because we've got the possibility of identifying potential for liquefaction from screening methods and mainly from the state parameter approaches, and we have a variety of ways of doing that. The second option for the CPTU, for my surprise, was the field vein test, and I'll try later on to discuss that a little bit further. Of course, that the choice for the CPT vein or any other of these penetrometer tests or shear tests, they've got to do or you've got to use them with due recognitions for rate effects. And this is generally done by this normalized velocity, which is a dimensionless parameter that can be expressed in different forms. But the recognition for rate effects is not straightforward, especially in the vein and certainly in the SPT. The SPT still have some use in different countries. You've seen some answers from Japan saying that they use that on a regular basis as a sideway from the main approach of using more advanced analysis. There was one answer on the cyclic flow penetrometer, but although this was a single answer, I'm going to sort of give some consideration to that, because I think this is a very promising technique, and we're using that in terms of research these days in Brazil and geophysics in general. So how these methods can be used, and going back to the actual definitions of undrained shear strength, we can rely, as I have mentioned before, on critical state soil mechanics, which is pretty straightforward and knowledgeable these days. And departing from these principles, there's a number of different ways of deriving the residual shear strength from the normalized cone resistance together with critical state soil parameters. This is a very consistent approach. It's representative of large deformations, but and require both field and lab tests, as I have mentioned before. But there are several uncertainties that are actually associated. Yeah.
Could you please wrap up your presentations, because we already have spent 15 minutes. So for the sake of being on the schedule, could you please go to your conclusions?
I'm getting there. So this is one type of approach, and then another attempt, and that's going from the residual strength to the liquefaction undrained shear strength. That's a bit more complicated because then we would have to rely on case-based studies. And again, there are several uncertainties in respect to that, and I can highlight that in the future discussion. And I really believe that if we have that as a key design parameter, that should be a measurable parameter. And among the different ways of the different alternatives, as I had mentioned before, I think that the most important one that we can really have close attention in research in the future is to look at the flow penetrometers. This is one example carried out in Brazil by Odebrecht and Mentras. We've got the piezo ball and the T-bar. They've got different positions for measuring the pore pressure, for understanding the mechanism during penetration. And what you see here, that we can, from these, from performing different cycles, you can get the actual degradation. We can derive the peak shear strength at the same time that you can derive the liquefaction, the residual shear strength from this by cycling these tests in the field. So as I mentioned before, there are no standard procedures for deriving these parameters. We still need methods for measuring that in the field, and cyclic load in field tests is, in my opinion, the most promising technique. Thanks a lot for your attention.
Your microphone's off.
Sorry, I wasn't aware my microphone was off. So I'll ask all the following speakers to try to stick to the 10 minutes presentations that we already discussed at the beginning. Since we are already a little late in the schedule, please do so. Our following speaker is Dr. Arcesio Liscano. He's a civil engineer with more than 30 years of experience in geotechnical engineering, including research and teaching in soil mechanics. He's currently at SRK Company in Canada. Arcesio, whenever you're ready, please, you can start your presentation.
So, thank you for this initiative and for inviting me for this discussion. Yeah, I will focus on the laboratory testing to evaluate the undrained shear strength of tailings material, trying to answer the question 2 of this discussion. Yeah. The first thing is to define what is the undrained shear strength or loose tailings. The undrained shear strength is the strength of the materials at the critical state. That is the definition, the clear definition. And the undrained shear strength at the critical state is a function of the void ratio and the effective stress of the tailing. But the void ratio plays the main role in the undrained shear strength. So tailings are sand-like material. It's a sandy silt or a silty sand. In more cases, is more silt. So tailings can have different initial or the void ratio in the field for different stresses. That means that we can achieve different undrained shear strengths for the same effective stress. But tailing can have the same initial void ratio for different P primes. In this case, the same undrained shear strain is achieved for the different P0. That is the concept for the critical state framework. So if we define in this way the critical, the undrained shear strain at the critical state, where the people name the residual strain or the liquefied strain, then any laboratory test device that provides data to determine this value, the undrained shear strain at the critical state, can be used to evaluate this value. One of the problems here is the stress path. If you perform a compression triaxial test, you will achieve a SUR value different as you perform a triaxial extension test. The triaxial extension test will provide or will achieve a SUR value less than the compression test. From an engineer point of view, people can decide to use the triaxial extension, but in this case, we need a reference test to evaluate the SU in the lab. One of the answers to the question in the questionnaire was related to the Dyda simple shear test. But the Dyda simple shear test doesn't provide us sufficient data to determine the SUR value. The Dyda shear test provides a maximum shear stress in a point, in a plane, with the vertical effective stress sigma set here, but doesn't provide the maximum strength of the material. Yeah, this monotonic DSS is not able to evaluate the SUR at the critical state. Conventional Dyda shear devices. So, undrained monotonic compression triaxial test is now used for the limit equilibrium analysis. Is used as a reference test for the undrained shear strength of the tailings material. So, monotonic triaxial compression tests are performed in disturbed reconstituted sample in the lab because undisturbed sample is difficult to take here. But if we need the SUR at the critical state, it doesn't matter the initial fabric of the material. It doesn't matter if the sample is moist damped or abbreviated, because this behavior or this response, untrained response before the critical state, is not considered to evaluate the SU at the critical state. Yeah, so we can use the reconstituted samples to evaluate the SU at the critical state. So the initial fabric evolved to the critical state and not affect the critical state. We can look at the paper from Lee and Dafalias 2012 when they introduced the anisotropic critical state theory. So what is the effect of layering, very thin layer in the response in critical state? Well, that is one of the things that is room to research. Here's some examples from Karlsruhe SAN, and in this case, the results are from moist damping and abbreviated. You see here on the right that the behavior before the critical state is different, but they achieve the same point at the critical state for this relative density. Here are the basic properties to estimate what is the Boyd ratio. But both sample types reach the similar effective stress at large strain, so they are at the critical state. So if we define what is the SU of the definition of SU as the strain at the critical state, it doesn't matter what happened before. So here are the same sum, with different relative densities. And you see that this is moist damping, and they go to the same point or the same peak at full liquefaction. This is not full liquefaction, but they will achieve this point at the end of the test. So the fabric is important in the behavior before the critical state. But if you are using the results of the critical state, it doesn't matter that what happened before. So if this is the line that we need to estimate the SUR value in the lab, you see here all the results with different reconstituted methods, moist damping or abbreviation, they go to the same critical state. So the SU value monotonic compression test, that is the reference test. The position of tailings in the site is an isotropic, or they say a K naught, the position where what we have to do is to represent the undrained shear strain in terms of the mean effective stress. But normally the reference value is with normalization with the vertical effective stress. So this is a very known figure. You see here that for a triaxial test, you should perform a triaxial test. That's in the result that you achieve. That is in the PQ diagram. That is in the EP diagram. You see the initial state is here, and the undrained test go to the critical state. Here is defined the state parameter, and that is the difference between the initial mean effective stress and the final, the critical. That is the same here. If you combine these two figures, you come to this value here. You come to this value, to this expression here, and then you can express the SU P prime value as a function of the void ratio in the lab or the void ratio in the field. Yeah, this expression here is appropriate when this line, this critical state line, is a straight line with a constant slope. So what the people try to do is to determine the C value, the state parameter from CPT, for example, cavity expansion, yeah, to determine these values. But one of the problems of these values is what we obtain from this expression with this, for example, for this value of lambda, a K naught, and M 1.5, that is more or less for the tailings, very angular material. The value that we obtain for SU P prime are very optimistic. So one of the procedures is to estimate SU, considering lab testing, for example, lambda phi, and then consider case history values. Because case history values depend how the SU P prime from the case history value are evaluated, but these case history values give a low value from SU sigma prime. So some concluding remarks in trying to respond to this, the question is the reference test to determine the undrained shear strain at the critical state is the monotonic compression test. That is the common thing here. The undrained residual strain determined with monotonic triaxial test are greater than the case history values. So we have to take these results from the triaxial test very careful. So one way is to determine SU using results from monotonic compression triaxial test. So for example, they determine the critical state line and follow the approach from Jeffrey Fimbini in 2016. That is more or less the approach that I describe here, lambda, C, case history, and how the state parameter correlate with the case history. So it's a very difficult task to determine the underlying shear strain. But here, the message here is determine the underlying shear strain using a laboratory testing result. Don't leave the task alone to the in situ test to the CPT. Use laboratory tests and try to see to refer to the case history. This case history value, for example, are in the procedure from Jeffries and Bean are related to the lambda and C value. Is a approach that we are using in several projects. But one concluding remark here is that the SUR value is very close linked to the limit equilibrium analysis. If we don't do limit equilibrium analysis, we don't need to determine this value. So one thing is to consider all these tests that will perform to determine the critical state line to in the approach from Jeffries and Bean. Use this to calibrate and choose an appropriate constitutive model and perform numerical analysis. And in this case, you consider the stretch paths in the analysis. So that is my presentation. Thank you.
Thank you, Arcesio, for your presentation. Now I think we are going to have time to answer some of the questions and comments from the audience. I believe that all of the speakers are going to be shown in the same platform. In order to compile the questions from the audience, we will have the help from Antonio, who belongs to the Center for Geotechnics from the Technical University of Munich. Andres, can you tell us, please, if we have questions?
Thank you very much to all the speakers for the presentation. I was guiding some of the questions, and the first one that is related to the question one to Professor Ramon Verdugo and Professor Antonio Carraro, but other speakers might also answer. And the comments is there seems to be too many uncertainties in assessing, for example, the underlying shear strength, stresses. How can you or anyone give confidence to a dam operator, to dam owner, that the upstream construction method is fine?
Yeah, well, my point was that it's very dangerous, it's very risky, and probably the only way to solve it is through a very deep science investigation. But for existing dam, that is the solution, just more and more information from in situ test. But I will not suggest the construction of new upstream tailing dams. That is our impression, unless you are in a very arid zone without much pluviosion, almost nothing, and also in the places where you don't expect earthquakes. So these two are very important requirements. If you don't have earthquake, for example, in Australia or I don't know, some places in the world, South Africa, etc., and also in places where the climate is pretty dry. So in those cases, you may think to build upstream dams. Otherwise, I would not suggest it. Antonio?
I generally agree with Dr. Verdugo. I would just add that I think the point that we're trying to make when we're raising these questions about procedures is really about the quality of the process and the methods being implemented. We're looking at a group of materials, they are not within the realm of the easiest type of materials that we have to deal with. So we have to have high quality from beginning to the end of the process. We need to raise the standards across the board in such a way that we can actually end up with a process of design and analysis that we can actually rely on.
There is also actually a comment about the requirements in general for quality assurance and quality controls. They should be very high to maintain the desirable performance of the facility during construction and in general operation. Do you think that contractors have this capacity and expertise to deliver these to meet these requirements? And what would be the role in general of operators, stakeholders, and of course universities and consultants in helping, of course, the mining industry to achieve this and to meet this requirement? This might be to any of you who wants to raise the hand.
If nobody says anything, I would say that there was quite a bit in the responses that they were saying you have to do a good design for the upstream dam, which is true. You always have to do a good design, but I think this is secondary compared with the control in the field, and that's really tricky because I mean you cannot give rules that because sometimes these dams are built over many years. And as somebody was saying, they are part of an operation. They are not a construction. They are part of an operation. So there are things that happen over all these years that is going to be very difficult to be sure that all these tight controls are in place all the time. So I think this is probably the main drawback of trying to do one of these, in principle, already dangerous structures. You know, how you ensure that this is complied throughout, and the only way is to have an atmosphere in which all these things are very much in the mind of everybody involved. And for these things, you know, universities, these webinars and things like that are important, but still it's going to be very risky because it goes over a very long period of time with other priorities.
There is actually a comment adding some points to the answers that were just delivered by Professor Dr. Ramon Verdugo and Professor Antonio Jens. The comment is we need to be careful and reading of making broad statements that upstream dams are inherently flawed. Our body of work is spent characterizing the tailings after place. If you have any comments on what will be, for example, the conditions for a safe operation of upstream construction facility, what do you think? Any of you, please?
They have been mentioned. I mean, there are a lot of things that you can do to make it safe. The first one is to have a good beach that is going to deposit draining material close to the face of the dam to ensure adequate drainage. But even then, we are not saying that this. I don't remember the word that was in the question. We'll say that are more risky. Not they are impossible, etc., but they are certainly more risky than any equivalent design. And of course, you can do things. You can control the rate of raising of the dam. You can ensure that that there is in a adequate climate drying of the tailings close to the dam, so that you can compact. So there are a number of things you can do. But what we are saying is that you have to keep those things operating a long time. So I think they are intrinsically riskier than others. Not impossible. There are many have not failed, and many will never fail. But you need more to be more aware in this case.
Thank you.
Yes, yes, I will add that my impression is in our desk, we can do really a good design, but construction and operation, especially operation, sometime in the mine, they have problems and they cannot avoid, for example, to change the tailings with more fines than we wanted in certain places. And that's it. It's the operation. They have to survive. They have to maintain the mine working. So because of that, it's risky. That is the point. And we have a long time operation. Okay, several years, 50 years of operation. Can we expect in these 50 years or 20 years of operation some problem? And we don't have room for those mistakes in terms of geotechnical properties. So one possibility is always every 5 years or every 2 years, I don't know, to perform a field investigation in order to be sure that everything is okay. That could be one alternative. But my impression is intrinsically, it's risky.
Thank you. Please.
Downstream dams are not inherently safe. You saw an example of one failing because the foundation materials. In fact, often the foundation of a downstream dam or any kind of dam is the key issue in terms of stability. And I think the point that Chris Hatton was making in terms of if you have a good design mining operation relationship and you build the foundation of the upstream components in a very stable manner with strong and well draining and features, there can be a reliability that's achieved. And so there may be more additional challenges, but it is something where I agree we shouldn't just make blanket statements.
Thank you. There is a question about switching a bit the topic, about the undrained shear strength. And for example, how to determine the undrained shear strength if we might be, if the tailings material can have or exhibit different critical state lines because they are composed of different materials, sand, silty grain size materials. And exactly how can then, therefore, we derive or characterize this challenge of defining a value for the undrained shear strength?
So, I don't know, Fernando, you want to say something?
Yeah, no, you can start and then I'll follow up. There's no problem.
So, one way is to characterize the different materials, focusing the different materials. This is a very difficult task. And if the material has very thin layers, or the tailings are layering in very thin layers, so this is very difficult to characterize the material in the lab. So if you want to determine some type of behavior, if you can, for different type of tailing, for example, look at the fine content of tailings. If the tailings are from the same origin, fine content, and you can determine the different properties based on the fine contents, then you can determine the critical state line for different fine content. The fine content moves the critical state. The critical state. The fine contents at the deposition produce different initial void ratio with the compression, yeah, because the void ratio change with the fine contents. The best way is to try to characterize every layer, but when the layers are very thin, as Jonathan say in the presentation, this is a difficult task. There is a room, as I say, a room for research.
If I can add something to that, and I agree with Arcesio. I think that we agree about most of what has been said, even about the difficulty of deriving the shear and range shear strength. But as for the question, the one problem is really how to deal with soil variability, because of course that we would like to rely on lab tests in which the boundary conditions are properly controlled. But the problem is that these materials are highly variable. And that's one of the reasons why the CPT became the dominant technique. I think that as a starting point that precedes any sort of interpretation, we should carry out a large number of CPT tests and make extensive use of the state parameter approach. Because by doing that, we start to understand what the variability of the site is, what the conditions are, where the materials that are prone to liquefaction are located, and then you are starting to be able to make use of all the concepts that we have been discussing before.
May I add a couple of comments? I'd like to make two brief comments. One is a soil that has silt materials, non-plastic silt, sand, is very different than a material that you take that and you mix it together and reconstitute. So I think that it's very important to try to do high quality sampling and really understand the material and the layering and the fabric in situ. The second point is there are problems where the quasi-steady state and the strength of quasi-steady state is important. And obviously that depends on the phase transformation and that depends on fabric. So that's another important aspect where we have to be able to understand and capture the fabric effects as well as the relative density and the effective confining pressure. Thank you.
Thank you. We got the hint that this is the last question. The Q&A session is over. And I thank you, all the speakers, and please, Cesar, continue.
Thank you so much, Andres, for wrapping and for compiling these very interesting questions. Thank you to all the presenters for their magnificent point of views here, shared here with the audience. I will ask all of you just wait a couple of minutes. We need it in order to change the speakers who are going to deliver their presentations in the second section of this webinar. So thank you all for being here and sharing your thoughts with us.
Thank you very much.
Thank you very much.
Colleagues, friends.
So we will continue with the second session of this webinar, which will discuss two main questions. The first one, which is the third in the questionnaire that was mentioned several times during this webinar, is: in an upstream dam with zones of potentially liquefiable tailings, what would be the most appropriate instrumentation to monitor the dam for preventing flow failure? These questions will be answered by two professors. The first one who will deliver the presentation is Professor Roberto Cudmani, who is a director of the Institute of Soil Mechanics and Foundation Engineering, Rock Mechanics and Tunneling at the Technical University of Munich. Please, Roberto, whenever you're ready.
So I hope you can see my slides. Hello, ladies and gentlemen, colleagues all around the world. I welcome you to the discussion of question 3. In an upstream dam with zones of potentially liquefiable tailings, what will be the most appropriate instrumentation to monitor the dam for preventing flow failure? This is the question. Some of the participants answering this question felt uncomfortable with the word prevent and indicated that instrumentation or monitoring alone cannot prevent a failure. I think that the word prevent was used in the sense of forecast or warning. A more precise formulation of the question could be, in an upstream dam with zone of potential liquefiable tailings, what will be the most appropriate instrumentation to monitor the dam and warn of flow failure? I think the people could feel more comfortable about this formulation of the question. In a more general sense, we could state the question, does monitoring enable a reliable warning of flow failure? Because at the end, it is not only the question of choosing an appropriate instrumentation, but even to see if monitoring is able to deliver an answer to this question. In my short presentation, I will evaluate the answers. Then I will show exemplarily factual evidence supporting the position that precursors or flow failure can be identified by monitoring. However, tailing storage facilities are complex geotechnical structures with considerable heterogeneity and spatial variability of material composition and state, as we hear in the former presentation, and not fully understood material behavior, complex construction history, which affect the behavior. For this reason, interpretation of the monitoring data, especially when different instruments and monitoring techniques are used or combined, poses a tremendous challenge even to engineers or to experienced engineers. I will finish my presentation with a rough concept to overcome this challenge in the future. We got 48 answers to the question Q3. The opinion of 75% of the participants is that monitoring can help to forecast flow liquefaction, while 25% of the participants will not rely on monitoring to judge the risk of flow liquefaction. Main arguments of the later group were the brittle nature of flow failure, the lack of technology to measure minor deformation, the inability of monitoring to identify triggers and failure precursors, and the difficulty to interpret monitoring data in complex geotechnical structures such as TSF. From the geotechnical point of view, the argument appears to be reasonable, especially the argument regarding the brittle nature of the flow failure as we hear in the last presentations. The participants supporting the usefulness of monitoring to forecast flow liquefaction argued that flow liquefaction will be preceded by deformations and development of excess pore water pressure, and therefore evolution of those quantities can be used as indicator of failure. They also state that monitoring will be useful only if the triggering mechanisms have been previously identified. They find that flow liquefaction can be forecasted by combining different monitoring techniques and field tests. That forecast is only possible if automatic and continuous recording devices are used. And few participants state that to assess flow failure, well-designed monitoring networks in combination with sophisticated data and predictive models are required. I really like the last bullet point. Different monitoring techniques and instrumentation as piezometers to continuously record phreatic level, water level changes and excess pore water pressure development, tiltmeter, inclinometer, extensometer to monitor deformations inside the dam, remote sensing and terrestrial survey to monitor global deformation of the impoundment and the slimes, accelerometers to monitor natural and induced seismicity, earth pressure devices to monitor total stresses and geophysical methods, as well as geotechnical field tests to monitor changes of density, water content, and aging effects were mentioned as required to monitor the dam behavior and to forecast flow liquefaction. Therefore, in my opinion, most of the participants knows or are aware of the monitoring techniques that nowadays are available. Now, some factual evidence. First, one supporting that there is no possibility to capture or to forecast flow liquefaction is the conclusion of the expert panel analyzing the failure of the Feijão Dam 1, also known, or the better known as Brumadinho. The conclusion was that none of the monitoring devices detected precursors to failure. Rather, the dam's failure was sudden and abrupt. Nevertheless, of course, this is the impression that everybody get when watching the video of the failure, that the failure occurred very, very quickly, and there was no possibility to measure anything in this short of the time. Nevertheless, in my opinion, this conclusion could also result from insufficient or not properly designed monitoring network, rather than a fundamental inability of monitoring to detect the failure. In a recent contribution, 2021, Grevy et al. Evaluate remote satellite INSAR data for a period of approximately 2 years before the failure of the Feijão Dam. The content plots on the left show the settlements of the tailings storage facility 8 days and 3 days before the failure. Red zones are the zones with the larger settlements. As can be seen, the increase and the changes of the distribution of settlement can be captured by the measurement. On the right, the authors plot the inverse of the settlements or the settlement rate, which is called inverse velocity, over time at different points for the observational period of 2 years. Decreasing inverse velocity with times, of course, indicate increasing settlement rate and therefore, in principle, unstable behavior, of course, assuming that the load is constant during this time. By fitting the points through by an inclined line, the authors roughly forecast the time at which the failure occurs, which is the time at which the inverse velocity vanishes. This is one interesting evidence that will show that, in fact, flow liquefaction does not occur as rapid as it was talked in the last presentation. Interesting is another publication for a couple of years early, showing the same kind of evaluation of INSAR data, in this case, Carla et al., 2019, for the Cadia gold mine, which also suffered failure, a flow failure. I think in this case, the triggering was a problem in the foundation, but still there was a flow failure of the dam. And if you see at the bottom, you see at the left, the increase of velocity with time, the increase of displacement with time, and the inverse velocity with time. And you see the method is also able to predict the occurrence of failure, or the time or the date of occurrence of failure, which is shown by the red line, vertical line. The same method was applied by the authors to describe also two kinds of failures, rather rapid, sudden failures. One of an open pit mine would kill 16 people inside the mine. You see the same behavior. And a very large landslide in China, which killed 100 people, also a very sudden event. This is, in my opinion, a very interesting evidence that, in fact, this kind of very sudden, very brittle failures can be in some way forecast by using, in this case, this kind of aerial sensing. So my concluding remark, different monitoring techniques and instrumentation are available, are well known by the participant in the questionnaire, but especially in the remote sensing and terrestrial geodesy, judge progress has been made in the last decade, as I was able to learn from my colleagues here from the university, which are developing a lot of methods to, for example, to track movement in the Alps here near Munich, using aerial methods, but also terrestrial geodetical methods. I think we should take advantage of that. Also, we know the US Army is able with aerial method to place, to attack object with very large precision. I think we have technologies that we are not using to control our tailings, to monitor our tailings, and could be used. Several reports of past failures conclude that available monitoring data was not sufficient or useful to identify failure precursors. We should look more in details in these reports. On the contrary, results of remote sensing data found in the literature provide some evidence of the initiation of a flow failure days and weeks before it actually occurred. And the question is here, is it brittleness an argument against the usefulness of monitoring, or is the brittleness in the laboratory directly transportable to the situation in the field? We have a system in the field which can distribute forces and is not failing as in the laboratory immediately. A sample, an element test is failing because all the points in the sample are experiencing the same stress at the same time. There is no possibility to distribute forces, but it is not the case in real geotechnical structures. We know that. However, tailings storage facilities are complex geotechnical structure with high material heterogeneity and spatial variability, and not fully understood material behavior, as we hear in the last presentations. Complex construction history. And in my opinion, in general, monitoring will be necessary, but not sufficient to forecast or prevent flow failure. Advanced compressive tools are required that integrate different redundant local and global monitoring data, field and laboratory testing data, numerical analysis of the behavior of tailing facilities, and past experience in a risk assessment and early warning system. We have thought about how such a system could look like. Because of the time, I will not go into details. I want to continue. Several components of such a tool are available and were developed at different universities and research institutes around the world. Some of them have to be developed or adapted based on interdisciplinary research with the participation of all stakeholders. It is important to get free access to real data. This is a sine qua non condition to develop and validate required tools. Due to its ability to learn and consideration of the history, the earlier the application of the tool starts, the sooner it will be available, the lower will be the uncertainty of the assessment, and that the higher its positive impact. In the development of such tool, and this is very important, geotechnical engineer, but not only geotechnical engineer, shall play a decisive role. Thank you for your attention.
Thank you, Professor Kutmani, for your presentation. We are going to move to the following one, which will be in charge of Professor David Williams. He's a full professor at the School of Civil Engineering at the University of Queensland, and he's the director of the Geotechnical Engineering Center within the same school. Professor Williams, please.
We went to the end instead of the start. Well, I'm going to be fairly quick because for me it's about 2:15 in the morning and I've had a long day. So I also changed the question around because I don't believe that we can use monitoring to prevent failure. So I changed the question somewhat to say, what would be the most appropriate instrumentation to monitor for potential flow liquefaction failure of an upstream tailings dam? And I want to start with this quote. Construction with or on liquefiable materials. And I actually asked Idris in 2020, what would he do about liquefiable tailings, given that he's quite an expert in that field? And he simply said, I'd avoid them. You wouldn't build a water dam using liquefiable materials or on a liquefiable foundation.
Excuse me, Professor.
Yes.
We cannot see your PowerPoint in presentation mode.
So, is that any better?
Not really.
Well, I don't know what else to do.
Can you please stop this sharing and start a new one?
Stop sharing and start again.
Yeah.
I don't think it's coming up now either. Oh, maybe it is now.
Can you please put your PowerPoint and your full screen, please?
Say that again.
Put your PowerPoint and full screen.
Can you see it now?
Yeah, thank you.
Don't know what happened last time. Anyway, so I also changed the question around so that I don't believe you can prevent flow liquefaction by monitoring. And then to go back to the point I was making before, so construction with or on liquefiable materials. And I asked Izzat Idris in 2020, what would he do about liquefiable tailings? And he simply said, I'd avoid them. You wouldn't build a water dam using liquefiable materials or on a liquefiable foundation. So why do we do this for tailings dams? It's not to say that upstream construction or upstream raising cannot be made to work. So let's think about upstream construction. It has limits, even in a dry climate. It'll eventually be founded on wet, soft tailings. So I've shown in the bottom of the screen a foundation. You've got a starter dam. We put in tailings behind it. It's got a pond somewhere down the beach. We raise it by the upstream method, create another beach with another pond, and so on. We keep doing this. Eventually, you have an advancing edge of a pond at depth, and as you advance the downstream crest, or as you advance your upstream construction, inevitably at some stage, that upstream construction, one of those lifts is going to have at depth a form of pond, wet, soft tailings. So there is a finite limit. So when someone, I think it was, I can't remember which of the speakers was talking about in Australia, where we've got flat country, we can make upstream raising work. And one of the reasons for that is that because of the lack of free storage, we don't have high dams. So let's turn to Brumadinho. It's been mentioned a couple of times already. It failed in seconds. It killed 270 people. So were there any precursors to the Brumadinho failure? There were piezometers, but they're actually standpipes, open standpipes, and they're relatively slow to respond. So you can do a calculation that in sand tailings, you might get a response in minutes. Let's say you're trying to measure a 1 meter rise in the phreatic surface. It could take minutes in sand tailings to get that amount of water in an open standpipe. In fine tailings, it might be days, but in the slimes, it might take a month. So they're not instantaneous. In the case of Brumadinho, those open standpipes were being replaced by vibrating wire piezometers, but all they were doing was putting them down the open standpipes. They weren't necessarily grouting them. And they were looking to automate them, but they hadn't actually got to that stage. So vibrating wire piezometers that rely on pressure changes will still be impacted by the rate at which water flows through the tailings, but they'll be quicker in responding compared with open standpipes because you don't have to fill a volume. CPTU, poor pressure dissipation, they showed that we were at about 50% of hydrostatic. It wasn't a hydrostatic water profile, it was about 50%. Inclinometers, unfortunately, they weren't fixed at the base, so they were sort of floating, if you like, and they didn't give an absolute measure of inclination. The survey monuments and the total station, insufficient precision. The station was located on the other side of the valley, too far away to get precision, and no one had actually done a closure to make sure they gave a sufficient precision. The ground-based radar that was installed for part of the time had noise associated with moisture in the soil and moisture in the vegetation and variable vegetation. And it actually showed no discernible deformation. And we were able to check that by checking it against the concrete lined channels on the dam that didn't show any movement. Whereas the material either side, the open material either side was actually going up and down. That was the noise. Seismographs, there were no earthquakes or blasts, although they did, of course, show the failure response, and they also showed the effect of the horizontal drain that was placed about 7 months earlier. And of course, the video cameras, most people have seen the front one. There was also one at the back. They didn't show anything before, but they certainly showed the deformations on failure. There were satellite images. They weren't analysed at the time, they were analysed after the event. They showed ongoing creep and some wet season acceleration. But what happened was sudden catastrophic failure, and it took place with no apparent precursors. So this is like what we got from the Dam 1 front video. If you look over time, in a very short space of time, just 3.6 seconds, you can see that development of that failure. Contrary to what you might have seen on the video, it actually started to move at the top first. So the crest went down first. Then a bulge appeared about a third of the way up. And gradually over time, the crest settlement and the bulge tended to merge. This is some of the data from the INSAR. It's not looking at it over time. It's just looking at a series of quarterly movements. And you can see the general trend of the movement. As you got towards the dam itself, there was movement both horizontally out from the dam and also vertically. And if you went back into the dam, most of the deformation of the slimes was actually consolidation. It was almost vertical. So, what monitoring may give warning of flow liquefaction? And the first point I'd make is above all that you should design, operate and close a tailings dam, ensuring an adequate margin of stability against geotechnical failure. It's the marginally stable dams that fail. Not all dams fail, and many don't. It's the marginally stable ones that do. None of the currently used monitoring techniques for tailings dams provides an adequate, that might be a nominal 24-hour warning of failure necessary to evacuate people at risk downstream to avoid or at least minimise the loss of life. There is a need, and this has been brought up before, install redundant monitoring systems, record and analyse in real time, and link them to triggers that interrogate the data and analyses and lead to emergency responses. Since flow liquefaction initiates within the potentially liquefiable tailings, focus on instrumentation of that zone. So don't just look at the face, don't rely on piezometers that might have a slow response. Look at things, new technologies like including embedded fibre optics, which could be placed on the beach before you put in the upstream raise, smart sensors or smart geotextiles, maybe microseismic arrays, which could be placed in the tailings prior to each raise. And that's the end of my presentation. Thanks very much.
Thank you, Professor William, for staying up so late and sharing your thoughts with us. We're going to move to the following question, which is question 4, that has to do with is it correct to evaluate the stability of tailings dams using the limit equilibrium analysis? If so, what would be the acceptable factor of safety for static and pseudostatic conditions? This question will be answered by 2 specialists. The first one is Luis Valenzuela. He's a civil engineer with a Master of Science in Fluid Mechanics from the Imperial College. He has more than 40 years of experience as a geotechnical practitioner. So, Luis, please.
Okay, shall I share my presentation? Can you see my presentation?
Yes, everything's okay.
Good morning, good afternoon, depending where you are. Thank you to the organizer of this webinar, very interesting one. I would like to rewrite my presentation after hearing from the preceding presenters. The question I was asked to answer is the one you are seeing. That I have a problem. It seemed to be a very easy question or very straightforward question to respond, but there are a few concepts that make difficult a quick answer. The one is the word correct. I mean, I would say there are always several methods that can be used, and you can use more than one method. And the correct is not simple to answer, because depending on the role or that you can give to your limited analysis, how are you going to use it in order to see what is the best method? And the acceptable factor of safety also have another complication, since as we will see on the next slide. I can run it. It's not moving. Why the limit is so popular? Because it provides an indicator which is called factor of safety that is easy to communicate and to understand. And I say, do we? Because there's several implications on the way to understand what factor of safety really means. It's a relatively simple calculation. Few conventional geotechnical parameters are used that the engineers feel comfortable with them. There are more 60 years of experience data that has been built, what allows the engineers to refer to past experience. Safety limit equilibrium analysis are required by several regulators, are relatively simple to obtain, and it's a method accepted by many regulators. It's a very useful tool as a pre-design or a screening tool, but also in many cases as a design tool. There are some drawbacks of limit equilibrium limits that are mentioned. First is that the method doesn't consider deformation, and deformation incompatibilities could be produced, especially if soil mass analysis is too heterogeneous, especially if you have a strain softening soil as part of the critical sliding surface. So you can get acceptable factor of safety for sliding, but could be obtained associated to unacceptable deformation. So you have to go to different method to complement the deformation analysis.
Luis?
When a strain softening soils are present, their residual strength is used, but the deformation could be important and must be analyzed separately as explained.
Do you hear me?
Yes.
You are showing the presenter mode. You are not switched to presentation mode. So if you may change it.
So nobody has seen my.
Yeah, we have seen it, but the other view, if you like. Now is correct. Yeah, you can go on.
Yeah.
Thank you.
Okay, I just was mentioning the drawbacks of limited equilibrium method. Limited equilibrium method had been questioned when liquefied soils are the main basis for dam support. The common general answer has been to consider residual strength for strain softening soil, and we have a lot of discussion on the different difficulties about this and the different methods you can use. But entailing some additional consideration could be necessary to do. I mean, not just to take residual strength. The variability of the tailings material has been discussed by other presenters. It's a major problem as well. I have to go quick. Oh, sure. Sorry, Cesar, I cannot change the slides if I put the presentation mode. I don't know why. Okay. In order to analyze the use of limited equilibrium method on stability, I think we should consider that there is a trend from going from a relatively simple method as the limited equilibrium method to more sophisticated stress deformation analysis with different soil constitutive models. And even now, new methods are appearing, like being developed as the material point method that is still in development, but it could be available for normal use in very short. And what we see is a tendency going from limited equilibrium method to a strain to stress deformation analysis and soil constitutive model. So it's a road, it's a tendency that the engineer is doing. And of course, together with the development or the more detailed sophistication of this stress deformation analysis, if they are made more friendly in order to use, it inevitable at a certain moment, limited equilibrium methods are going to be used for some specific cases because of their simplicity. But at the end, we will see that the tendency will continue to go for stress deformation analysis, as already happened with the seismic stability analysis. Seismic stability analysis was done with limited equilibrium method using seismic coefficient, and then the requirement came to use both limited equilibrium method and stress deformation analysis. And now there are certain institutions like the ICOL that is suggesting to go directly to stress deformation analysis. But there is an exception in that tendency, which is the use of rational selection of seismic coefficient. For instance, the one proposed by Professor Bray that was a comment at the beginning of today. What does a factor of safety bigger than 1 means? Does it mean that the dam is safe? Limited equilibrium consider first, we have to say limited equilibrium method consider only one specific failure or mode, sliding. So you cannot say that because you have a factor of safety bigger than 1, your dam is safe. The other thing is the stability margin, which is the difference between safety factor and 1, is expected to cover calculations and properties uncertainty, plus a certain clearance to assure a low probability of failure. But probability of failure is not provided by the method. Reliability index can be calculated with limited equilibrium method. So in order to compensate or to consider the variation on the parameters, and some relations have been proposed in order to have a link between the reliability index calculated based on the limited equilibrium with a probability of failure. And it will be shown on the next slide, but we should remember that probability of failure depends also on the design and construction quality, as we will show on another slide. In critical cases, probability of failure replaces the factor of safety as an indicator of acceptable stability. For instance, in cases of a high failure consequence. Here is shown the relationship between stability analysis by limited equilibrium that with two degrees of certainty or uncertainty in the parameters that could be compensated working with the reliability index, which depends on the values, the factor of safety that you have calculated based on the more credible or the parameter you consider the best, -1 divided by the standard deviation. And this reliability index could be related to probability of failure, assuming a certain distribution of probability, in this case, the normal distribution of probability. So there is a way that in certain cases you can go from limited equilibrium to an estimate of probability of failure that could be very useful when you are dealing with projects that in which failure could have serious consequences. In that case, as I said, the probability of failure replaces the factor of safety as a measure of the adequate stability or adequate safety provided by that particular project. But as I said, the probability of failure is also independent, is also dependent on the design and construction quality. And this is an empirical work done by Silva and others that explain that it showed that this is empirical, not theoretical. You cannot use for calculation, just to show the concept. And you can have a factor of safety, calculated factor of safety by limited equilibrium analysis that give you 1.5. But that 1.5 is not the same for a dam or that is not very well designed or very badly constructed to one which is good design and constructed as following design and quality control, etc. So we could have a tremendous difference on probability of failure just because on how we build. This is based on water dams and not tailings dam, but the concept is the same, and it takes our attention to the impact or the tremendous impact that the poor construction quality or poor construction have on the probability of failure that is connected to that factor of safety that could be considered acceptable because it has a larger number, 1.5 generally is considered an acceptable factor of safety. But because of poor construction, you could be dealing with a very high probability of failure. So let's see a bit of limit equilibrium method in tailings dam now. A static condition usually could be applied on any dam, but we will see that we have some restriction for upstream tailings dam. But in general, these are the type of...
Luis,
yes?
Can you hear me?
Yes.
We are on time, so if you can start wrapping up your presentation.
Yeah, okay.
The final comments, please. Thank you.
Yeah, the same is well done, the seismic condition and examples of the factor of safety that are used, against not directly related to the problem we are facing. And this is the case of upstream tailings dam. And the first clarification I want to make is that upstream tailings dam could have a different geotechnical and engineering characteristic, but it's still using the upstream contraction method. So it has been confusion in the discussion and even in the regulators and the laws when, for instance, some country has banned the construction of upstream tailings dam because they were thinking on a simple upstream tailings dam as the one that we use in the old Chilean upstream dam that have the tremendous disaster of El Cobre in 1965 with more than 250 casualties, and also Brazilian Brumadinho, which are characterized by relatively steep slope, high rate of raising, no tailing segregation, potential liquefied tailings. Limited equilibrium method probably could be used for analysis of existing dam as a first step, and also for screening purposes when you are thinking about the possibility. But difficulties in defining soil characteristics due construction and operation variability that has already been discussed, stress deformation analysis with adequate constitutive soil model probably will be necessary in order to advance in the study. My personal opinion that coincides with several of the opinions that were given in the first section is there are low chances that this type of dam be acceptable to the difficulties in soil characterization, high dependency on operation procedures, difficulties with monitoring that would allow required time for emergency response, and questionable walk-away closure. I think it's almost impossible a walk-away closure. But there is an improvement upstream tailings dam that are completely different and that are built in an adequate site where you don't have too much rain, where you have a flat land that could allow you a low rate of rising, and seismicity is not as big. In these cases, the climate could help on desiccation effect, and if you use, and that together with segregation of the bed could help you on compaction of part of the tailings and the use of gentle downstream slope. This type of upstream dam has been built in Canada and Australia and other countries. The limited equilibrium method could be applied by detailed geotechnical characterization is required, as well as strict construction and operation procedures should be established. Eventually, stress and deformation analysis is also needed. Operation control, as it has been mentioned, is the main issue in these dams built in the mining. As we said, a limited equilibrium method will provide a factor of safety that has to fulfill the local regulation and international guidelines, but dependent on the level of failure consequence, failure mode analysis, dam breach analysis, and probability of failure analysis must be defined. In those cases, probability of failure and not factor of safety is the indicator of safety. Thank you very much.
Thank you, Luis, for your presentation. So thank all the audience for keeping up with us during this seminar. We get to the final presentation now in charge of Dr. Mike Jeffries. Mike is a consulting engineer with some 45 years of experience, perhaps most known for the state parameter approach to soil characterization and the generalization of critical state theory. He's very well known for his book on soil liquefaction, which is now in its second edition, widely cited. So, Mike, thank you for being here with us.
Coming up? No. Yes, there. Okay, we're having problems with the screen share again. Okay, let me try again rebooting this one. Is that coming up? No.
Please put your PowerPoint in presentation mode so I can share your screen with everybody.
Present. Okay, try that. It's in presentation mode now.
Yeah, everything's okay. Thank you.
Have you got it? Is it there, Bruna? Yeah, you were there. Okay, good.
Yeah.
Thank you. Thank you for your patience, everybody. I'll try and be quick now. My task was really the corollary of the previous speaker. Should we go to the next generation of how we assess our dams? And really the context of this question is what is Brumadinho, what you're looking at here. And you've seen previous speakers refer to this, how we can suddenly go from an apparently stable dam to something that's developing in a matter of about 5 seconds into a flow slide. And that poses quite a challenge to our soil mechanics. And so the thought is, do we need to move to more sophisticated methods of analyzing? And of course, when you do this, people are talking about, well, we need to kick in stress strain theory. And then the next question that comes up, okay, what theory is appropriate? And before I tell you why it's appropriate, I've got to go through the elements of what is critical state theory. And it encompasses actually just 4 ideas. The idea at the top is soil is plastic. That is, we can use the mathematical theory of plasticity and it will apply to soil. And that means we break strains into 2 parts, and it's a simple linear decomposition. And we then say that it's only the plastic part that dissipates work. The next step is we have a unique critical state for any soil. Yes, speakers have mentioned it can vary with gradation, it can vary with mineralogy, a whole bunch of things. But for any particular soil, we have a unique critical state. And by unique, I simply mean it's a single valued function of the principal stresses. The corollary, if you like, of a unique critical state is that a soil will move to its critical state with distortion. As you shear a soil to distort it, it will move to its critical state. We actually, this is a very nice idea, but to make the idea tractable, we actually need to put a little bit of mathematics around it. So we say, we will define a void ratio deviation measure, which is the now famed state parameter, which is a simple void ratio difference. And then regardless of the details of your critical state locus, you can just say as the distortional strain goes to infinity, the state parameter goes to 0. And that simple statement, which is implicit in Casagrande's work from, I think it's 70 years ago, that allows you to build the mathematics of what's going on. And the final step in the analysis was down to Don Taylor, and it was Alan Bishop who put it together as an equation, is we say that Tertzagi's understanding of soil strength is wrong. In fact, the mobilized friction angle comprises a critical state friction angle and a dilatancy. And the dilatancy then gets linked to the state parameter. And this framework has been known, or the elements of this framework were in place in 1950. So as a profession, we've known these ideas for 70 years. Now, it took a little while longer for the mathematics to be pulled together. And I put the date down the bottom of the slide saying, well, pretty much by 1990, all the math was in place. So we've actually had this comprehensive understanding has been available to us for 30 odd years. So why is it appropriate? Well, it's appropriate because this framework, is usually called critical state theory. It's the only framework with a physical basis for how void ratio controls soil behavior using consistent physics and mathematics. You know, there's nothing else out there. Now, it may be in 20 years' time, something will come to pass, but right now, this is the only game in town. If we're going to understand these twice, if we accept that void ratio matters, then this is the only game in town. So that's the framework, but there are a range of models within the framework. The framework is universal. It is a set of ideas and it's a set of observations, but we then want to make it mathematically tractable. And various groups have done this. I've thrown up on the right-hand side here, I said, actually, if you go to a current software package, and this stuff all has to be implemented in software. So it's unusual to you, it's not available in software. And you find bounding surface implementation, which is Yanis Defalius and co-authors, and there are various versions of this. NORSAN, which is a generalization of the Cambridge ideas. And then we also have the clay and sand model, which is the Barcelona folks kind of like. And the linking feature of all of these use the state parameter. So that is, they're all critical state models, they've all got a critical state, and they've all got the state parameter. The properties they use are common, but they're named different in the various models. So that's something perhaps we could think about cleaning up. But the power of these models is illustrated over on the left-hand side here, where I show a stress strain curve and a stress path of obviously a very catastrophic liquefaction. And blue is what the theory computes, brown is what was measured in the lab test. And we honor void ratio while doing this. So that's what it's all about. So we now want to pull this into an analysis. So we're going to implement it in finite elements or finite difference. And the important thing for us as a profession is this stuff has now moved beyond universities. It's now available in commercial software, and at least 4 standard commercial platforms have implemented various forms of critical state theory. What you're seeing in front of you here is the implementation in Plaxis. And it's not just a question of saying, well, I've got a software package with a critical state model in it. In fact, there's a whole methodology that comes with it, which I'm circling on the left-hand side here. There's a protocol for how you measure the mechanical properties. We still rely on the CPTU as the principal method of site investigation, but we now process that with a formal inversion, and that's where we get the state parameter in situ from. And we actually also include soil variability. So we have this notion of characteristic state parameter to allow for the uncertainty in it. And we have to use large strain mode, as it's called, because that way we can start seeing the mechanisms. And what I'm going to show you now is how this all works. What you're looking at here on this slide is you're going to see an upstream raise, which is going to come in on the right-hand side of the screen. An upstream raise will appear. The color coding is the mobilized stress ratio, or Q over P over the critical state friction ratio. And when it goes red, you're in the critical state. And what we're going to do is we'll watch the construction go ahead, and everything is drained. There are, just like Brumadinho, there is a zero and nada, rien, excess pull pressures until the last lift. And we put the last 500 millimeters on rapidly, and we then see what happens. And what I want you to do when you see the simulations, look at the toe of the slope and then watch what happens. So here we go. It works. We're building the thing now. Last lift gone, and we just failed at the toe, and we're now propagating outwards. And notice how the crest is settling. And isn't that just beautiful? And doesn't that look like Brumadinho? Now, the theoretical rate at which you saw that propagation go outwards is 50 meters a second or thereabouts. That is exactly what you see at Brumadinho. And you'll notice a settlement here. Oh, you can see it there. This you're looking at was the first run of this particular case history. And 4 meters of settlement was computed. The actual is 5. We need to tweak a couple of things, but this was a validation. We wanted to see if we use things at face value, just how well it would work. And the answer is here. We haven't input an SU. We haven't input an SR. We've computed everything directly using consistent mechanics. And we get everything right. We get the distance of the propagation right. We get the settlement right. We get the propagation velocity right. We get all the details. And I've titled this slide Communication, because the point I want to make here is this is a very pretty slide. But you think of when you got up this morning, you probably looked at the weather on your the TV to look at the on your news program, that you'd looked at the weather forecast. And people show how the weather is going to evolve during the day. Well, what you can see here on your screen is I can describe to a board of directors of a mining company. I can show regulators what's going to happen, and I can even show the general public. I can communicate what is going on, and I can also run different scenarios and demonstrate how these things can happen. This is, to me, one of the wonderful things about this kind of numerical method is, yes, it gives us more insight as engineers, but also enables us to communicate better. And I emphasize this is done with commercial software. This was done with Plaxis. Moving ahead, a number of speakers have talked about the foundation. What you're looking at here is Cadia. And this is the mobilized stress ratio. And now when you read, you're very close to the instability limit. But Cadia was actually killed by the foundation. It was the foundation. So here we have the tailings, which is the stuff in green and blue, and the red is the tailings at its instability thing, and it's about to liquefy. But it's not blown the dam apart. The dam moved because the foundation failed. Now, you'll find people say that critical state theory is wonderful for non-structured soils, but it can't work with structured stuff. Well, the foundation here was a residual soil, and the data, or the inset showing the stress strain behavior, was measured on undisturbed samples of that residual soil. And the brown is what was measured. And if I hadn't told you that was residual soil, you would say, oh, that's another loose sand liquefaction. The blue is the fit of critical state theory to that test. It's beautiful. And the key thing here is, other speakers have mentioned foundations, but in terms of actuarial numbers, half our so-called liquefaction case histories are actually foundation failures. And you've got to deal with strain softening in the foundation and think about its consequences. So to quickly come now to an advocacy of why I believe this approach is the future for our profession, I'm going to break it into what's good and bad about finite elements. What's good is it's actually quite simple. We're using all data at face value, and it's consistent mechanics. There's no K sigmas, K alphas, or other things. There's no fines content corrections. You do everything much the same as you would do, for example, in hydraulic engineering. It's all proper mechanics. And it gets all the details correct. We get strain softening. We get the magical drain to undrain transition. We don't have to invent it. It's actually part of the mechanics. And we explicitly honor void ratio. And we have a track record of forensics of large dam failures. When something bad happens, there's always a search for the guilty. The search for the guilty in the last 20 years has pretty much always required finite element analysis. So that's the good part about finite elements and critical state theory. What's bad? Well, the previous, Luis was referring to all the experience we have with factor of safety. We have not built a similar body of experience or understanding around finite element analysis. We've applied it to dams that have fallen down. Well, there's no argument what the factor of safety was. They fell down. But when we start applying this methodology to proposed raise or trying to assess the stability of an existing dam, we've got to get our heads around of how we're going to represent safety and how we're going to communicate our assessment of that safety to the mine owners and to the regulators and to the general public. So we have some work there. I have to say, I don't believe that these finite element things, they're packaged in nice modeling packages, which you can put on, you can compute your screen, or you can build things and whatever. But to me, they seem less than easy. The things like getting the right K0, it's not as easy as you may think. So it's there are some issues. I don't believe our software vendors have quite got us to where we'd like to be. At least this methodology is not as easy to use as limit equilibrium, and that's, to my mind, is something the vendors are going to have to pick up on. But the biggest problem is education, and I think it was Antonio mentioned that in his talk that perhaps the practitioners were not educated enough. And what we have here with finite elements is a very sophisticated thing, and it can represent a lot of detail of soil behavior. But if the people asking for it or trying to use it don't have the required understanding, there's going to be a problem. And the problem really comes down to the education. And the suggestion, I think, from Antonio was perhaps practitioners need to get smarter. Well, my response is this. We're in this mess because of the universities. This book, I'm sure you'll recognize the title, and you'd recognize the photo of the two criminals who produced it. The preface of this book and I've taken a couple of words out so I can get it on the screen, but it says research in soil mechanics diverted attention from the manifold limitation imposed by nature on the application of mathematics to earthwork engineering. That is, soil is some magical material that is somehow immune, or applied mechanics doesn't apply to it. Mathematics cannot work with it. Well, to me, this is an appalling statement. And the problem is that this book has influenced most university teaching and most university curricula. And the consequence of this total utter abrogation of mathematics is this: the physical basis of why soil behaves as it does has deliberately not been taught. And that is why us practitioners haven't had, or are perhaps struggling with some of these ideas. It's because we are dealing with a complete, utter failure in geotechnical education. So, to quickly wrap up, Mike's answer to question 5 is yes, we do need this method of analysis. And I believe it has to be used more widely. It's not just in terms of finite element analysis, the ideas of, which is implicit in the question, but understanding that a theory of why soil behaves as it does, you can use that to look at a track soil test and say, oh, does this test make sense? What is the test telling me? Having an understanding of soil behavior, to me, has to become a core competence for all involved in tailings engineering, as it's now called. And I say the corollary is that the real question 5 should have been, how do we fix geotechnical education? At that point, I'll now put on my bulletproof vest and over to questions.
Thank you, Mike, for sharing that very important message at the end of your presentation. Very important for all of us who work both in academia and in practitioners.
So who's going to shoot me first?
So now we have time to answer questions from the audience. I will remind you that all of you are encouraged to give your opinion regarding which of the topics that were presented today are most pressing for the geotechnical practitioners in tailings engineering. Remember that this will be taken into consideration as a valuable input for the technical committee to guide its following activities in the next months. So if Andres is there,
okay,
let's
start. Yes, actually, I thank you all the speakers for the nice presentation. I was reviewing the chat and I saw that Professor Williams was very active, and actually one of the questions that was done there and actually is addressing the very challenging and controversial topic of monitoring and the role it might play on forecasting flow liquefaction. One of the questions is, for already existing upstream dams, which are not adequately instrumented, what monitoring system would be beneficial to forecast failures in future in terms of liquefaction? What are the alternatives, or there are no alternatives?
Well, I think the comment I'd make is that we need to get to where the failures, those sorts of failures tend to initiate. It's not right on the face. It's somewhere in the body of the tailings. So that's where we need to start putting instruments. So we need to develop instruments that are suited to embedment within the tailings body. So we can pick up sometimes subtle movements as they happen. Yeah, if you wait until it appears on the outside face, it's too late.
Yes,
I think we need some new techniques.
I think it is very critical. We were discussing with you, Andres. I gave you a very simple example, and I mentioned if I tell you have a shallow foundation, and I give the load of the foundation, and tell me if this foundation is stable, you will have a very big problem, and probably if we ask 10 people, we will get 10 different answers. The answer will be much more precisely if I will give you, for example, the settlement history of this foundation. And this is the problem when we have a tailing which is already existing, and we do not know really the history, the construction history, and the deformation history of this tailing. It's for me a dangerous topic. Of course, you can try to install instrumentation, but we know what happened in Brumadinho, where people were installing some things in the dam just when the dam failed. So it was a failure of understanding that the system was in such a critical state. And this is what we have really to try to judge. Is very difficult. What is the situation of the tailing? If the tailing does not allow a clear assessment regarding safety, I will say we have to try to monitor the tailing using remote sensing, because other method could endanger people. Only if we are sure that these tailings are in a safe, in a limited, relative safe state, can lead people to install other kind of monitoring. And of course, we can imagine a lot of kind of monitoring which can be appropriated for this case.
I think also though you need to fix on the basic premise that it's marginally stable dams that fail. The majority of dams, in fact, don't fail, but too many fail. And the ones that fail are the marginally stable ones. So we need to get away from a situation where we've got marginally stable dams. And there was a little bit of chat, or some of the questions that came up before, that some of which I attempted to answer by writing responses. And this idea that we can design a dam to be stable even if it goes to the post-liquefaction strength or the post-seismic strength or whatever. If you have to go to that extent, I think you're in all sorts of trouble, because you look at something like Fundão or Brumadinho. When you had flow liquefaction, it's got virtually negligible strength. It's got the sort of strength it had when it went in as a slurry in the first place. It's negligible. No dam is going to stand up if you're going to design it for post-liquefaction strength. It's just ridiculous. So we need to get to a situation where we don't have that situation. We don't have marginally stable dams. And we do it much better for water dams. We need to do it for tailings dams as well. We need to question as an industry why we're not doing that. Actually, Lewis, I learned a lot from Lewis about the Chilean situation. That's a good story. The earthquake of the El Cobre failure that killed a similar number to Brumadinho led to a real change in the way they manage tailings in Chile and then Peru as well. Fantastic story. Should be told more. That's what the rest of the industry needs to do.
The problem there, David, is we're dealing with some legacy dams.
Yes.
Going forward is straightforward, but we have large legacy dams.
Yeah, even legacy dams, though, in the case of Chile, the abandoned and closed dams actually perform reasonably well because they've drained down, because they've got a very dry climate. But legacy dams in somewhere like Brazil, a real problem.
Having said that, it strikes me when I read Brumadinho and all your work on that, that if the dam had just been left alone, it would still be there and it would still be improving.
That's debatable. You could argue it a different way. You could say that while they were operating the dam, they were managing water and other things. When they stopped operating the dam, perhaps they weren't managing some of those things.
But the piezometers show declining pore pressure.
It showed a declining water level. Yes.
Yes.
They weren't measuring suctions.
It was getting better. Soil behaves according to stress ratio. And the stress ratio is Q over P. If P is increasing, eta is coming down, everything is getting better.
But you got to take account of what's happening above the water table as well. And there was essentially a disconnect between the two. It was wetting up from above while the water table was slowly going down, which was also a consequence of them having quite a bit of seepage coming out of the dam. So complicated case, but
it strikes me also there was a complete failure of understanding, because you refer to the horizontal drain drilling, and when I read in the expert report and when I first read the report, the hairs stood up on the back of my neck. I thought it was very close to failing the previous year. And how anybody can be so stupid to observe that response and then go and do it again. It frankly beggars belief.
Yeah.
And that to me was a failure of engineering judgment. And then I come back to my point about education. You know, and all of us are, you know, quasi experts here. We know our subject. But if you're a mine manager and you go ask, well, how I want some engineering company to help me, I guarantee you, if you put out 5 requests to 5 different engineering companies, everyone will say they're an internationally acclaimed expert, well suited to the task.
And you get 5 different answers.
And you do. And this then gets back to, if you look at the ICMM, they say, well, we're going to have a core competence. But it's for us to define what that core competence should be. And that's where I think this committee needs to go is, okay, what is the core competence? What is the core knowledge? And that was my point about education, because a lot of this stuff just doesn't, the required competence does not exist within the current consulting engineers. So how are we going to fix that?
Education by the right people, to the right people.
Yeah. The corollary I would say is we need to start running some courses and get the universities to do continuing education courses.
Well, I'm not convinced, because I've had a bit of experience of lecturing outside of the university sphere as well, and it was a much more, in many ways, a more pleasant experience than doing it through a university. So you can't guarantee that all the world's expertise sits within universities. I mean, you're not within a university. So there's a lot of talent out there not connected to a university. And if you were looking at just one university, how many tailings experts might there be in one university? You'd be lucky if there's 1 or even 2. So that if you want to run a high-level course in tailings, you should not rely on just whoever's within one particular university. You need a more global contribution than that.
Cool.
And if universities can't move quickly enough to do it, then other providers have to come in and start doing it.
Yeah, I will continue with some questions, and very nice discussion. Actually, moving to Luis. Luis, if you can also provide your view on the role of monitoring, but also about, you mentioned these constraints for type 2 dams in regulations. It is possible to enforce these type 2 dams in the existing regulations?
Well, not in the case of Chile. In Chile, Peru, and Brazil, upstream tailings dams are banned, irrespective of which type of upstream dam, which is, I don't think it was correct, but they took it the easy way and they banned all upstream tailings dam. But I realize that there are a few examples in the world that they can build upstream tailings dam, but using several operation and construction measures in order to help on the improving the characteristics of the tailings and also of allowing poor water pressure, dissipation, etc. So, but in those countries that is banned, I mean, it's banned. And the problem is what Mike was saying. I mean, well, it's banned today, but we have a legacy. And that is a more difficult problem than design a new dam. I mean, what to do with those large legacy dams in Brazil, mainly with the climate, the rainy country as they have. I'm in a previous debate in Brazil, I was presenting what has taken the people to insist for many years in building upstream tailings dam, and the answer, we suppose it was because they were saving money. I mean, they were using the less cost solution. But it could be shown, for instance, that in the case of downstream sand dams, if you compare the volume that the tailings are there are relatively similar, because in those downstream sand tailings dam, part of the tailings is deposited as a slime or tailings, and other part of the deposit is formed by the sand that is used to build the dam. So at the end, you end with a downstream dam that is taking care of all the volume of tailings that want to be deposited, but at a larger, higher cost, but not too much. I mean, it's the cost of compaction and the cycloning. I mean, it's nothing tremendous. So I think when this decision has been taken in building some of these tailings dams, as the one in Brumadinho, El Cobre, etc., they didn't look for that. I mean, they were just taking the straight decision based on less cost, independently of safety or stability, etc.
There's another thing that I could throw into the mix, and that is if your aim was to build a very robust dam, because these things are going to stand up forever, what you want to make is something that doesn't have a credible failure mode, so that it will be safe forever. If you really want to do that, you could build a very robust dam using waste rock. It's an open pit operation, you've got lots of waste rock. But you can only do that because it's more expensive to transport waste rock than it is to transport tailings. You can only do that if you put your tailings closer to the pit than you would normally do. So that might change the paradigm of how people lay out their waste facilities. So you might actually build a waste rock dump closer to build a waste rock dump close to the pit, but use it to store tailings behind. So the tailings actually ends up closer to the pit. So radical sort of idea, but because we set up, we set ourselves up to fail in a way, because we'll pump the tailings further than we'll haul the waste rock. So inevitably we've got to build a tailings dam out of something, and it'll be cheaper to do it out of tailings or out of upstream lifts rather than using waste rock, because the waste rock's too far away. So we need to start thinking about quite radically different, simple but radically different ways of approaching these things. I think we're too locked into what we've always done.
Can I add a thought here that compaction is what Luis says, compaction doesn't necessarily have to be to 95% proper. Just tracking with a bulldozer, which is a very few cents per square meter, can get you an awful lot. So I'm a great fan of using tailing sand with a little bit of compaction. And the other point I'd make is the US Army Corps of Engineers built the first liquefaction resistant dam in 1935. That's nearly a century ago.
So we can do it.
We can do it.
We just need to do it.
A final question, actually related to the question 5 that Mike Jeffries addressed. For this numerical stress strain analysis, there is a large demand of data in general. And we know there is always an interaction between designers and dams operator about reducing the amount of data the operators would like to pay for acquiring this information. How to manage these challenges of acquiring the required information for the constitutive models or the numerical analysis indeed, and to also address the challenge of uncertainty in general for the existing tailing facilities and the new facilities coming. What are your opinion how to address this challenge from a technical point of view, but also from this relation operator and designer point of view?
Right. I perhaps best go first on this one. The first thing I would say is these more sophisticated methods don't necessarily mean a huge change in our site investigation procedures or the number of tests. We're still going to do roughly the same number of CPT that we would do for limit equilibrium. The issues are the same. The only thing we add in, which might be slightly unusual, is some traxial tests on reconstituted samples. I've been retired now for 10 years, but when I was doing it, we would do a batch of testing for $10,000. Now, when you've got Vale, I'm sure right now they'd see $10,000 very cheap compared to a $5 billion liability, right? So it is not a huge data demand or a huge change in practice. The biggest change is consulting engineers getting their heads around the different type of analysis and understanding soil behavior. The biggest challenge is education. I keep banging on about this, but it truly is. The engineering costs will not go up greatly. And in a lot of ways, it's actually simpler because you don't have to faff around the K sigmas and K alphas and all the other garbage. It's actually simpler to do. So I just don't accept that it's an intrinsically more expensive proposition. I do accept for the current generation of older consulting engineers, they're going to be out of their depth. They need to get educated. But that's the challenge. Anybody else want to comment?
Well, I'd say that, I get to review a lot of designs, and I find that reports are hundreds of pages long now. So that it's not as if they don't have a shortage of data. They have oodles of data. They don't do much with it. The data's not, or the tests they do are not broad enough. So they'll focus, and typically they'll do lots of CPTs, not much lab testing. And then there's a mismatch between all that data and their selection of design parameters. Complete mismatch. If you try and relate the two, they're not related at all, I don't think, quite often.
Yeah.
And in fact, I think the design parameters are often just presumed based on what they selected last time. So I think investigations have become quite a bit more expensive, but they're not. That money's not being put to great use, or the best use that it can be put to. And I think we need the right mix of testing techniques, the right laboratory testing, the right analysis, the right field investigation. And I think too many consultants are taking the easy route and just doing cone testing. If they're testing tailings, they're just doing cone testing.
Yeah.
Not much else.
Yeah. I'd echo some of your points there, David, but I also think there's a generational thing going on. I have seen in the company I spent most of my career with, that younger engineers would take the CPT testing report and it became a report that would come in now from a specialist contractor, and it'd be bound in as an appendix. They really didn't look at the data. The older engineers of my generation, we were the ones who pioneered cone testing, and you'd find these 65-year-olds getting the data file, bringing it up to Excel and playing it with it on the screen of their computer. They were, just wanted to get their heads into the ground and see what it was telling them. Whereas the younger people, it's just another input. So I think something has gone missing. I always like to make the younger engineers bring the data up in Excel and plot the stuff up and then do the interpretation. Don't rely on the report from Contech or IGM.
Yeah, I think the younger engineers are a bit inclined to just press a button, and then the results they get out, they just believe. They don't interrogate them. And they do the same with stability calculations as well. They rarely look at, okay, where is this particular subsurface spending most of its time in? Which material is it spending most of its time in? That's the material you've got to focus on, because you'll get your biggest bang for bucks in refining the parameters of that layer. But they tend not to do that. They don't look at where the critical subsurface goes at all. In fact, they even generate, sometimes with non-circular, kinematically impossible subsurfaces. and yet they'll just accept them.
Yeah.
Well, the computer gave me this. I pressed the button, it gave me this.
Yeah.
Right angular bends,
We are close to the finish. Actually, there are many questions that I couldn't pass to the panels, to the panelists, but I think just to wrap up, thank you very much. And Ramon Verdugo is going to join again to make some final comments and discuss, of course, and comment on the role that the technical committee is going to play on all these discussions and the points that Mike Jeffries and Professor Williams were, all of the panelists were addressing. Thank you very much.
Thank you.
Well, thank you very much to the speakers. Some of you wake up very early, and David, I think it's 3 a.m. in Australia.
It's 3:30, almost 3:30.
Oops. Well, thank you very much for this extraordinary effort. I hope the assistants have enjoyed, as me, this webinar. This was very interesting discussion. It's not clear the answer. And I would like to ask you to, the assistants, if you can write in the chat, what would be the best topic for the next discussion. So TC221 will try to have another webinar in that topic. Thank you very much to all the speakers, to all the participants. Thanks a lot.
Thanks, everyone.
Thank you. Thank you.
Bye.
Thanks, all of you.